So are we ready to start, Adriano?
Yes, we are already broadcasting on Facebook.
All right. So welcome to this webinar titled Development of Mars, the Asteroids and Beyond. This is the fourth webinar in our pre-conference program leading up to the third SpaceRenaissance Initiative World Congress, which is going to be taking place in June. We have 6 presenters today, excellent people, excellent, very knowledgeable people in this particular topic. Our schedule is basically, we will have 5 presentations of about 15 minutes each, followed by one of Isaac Arthur's excellent videos, which is going to take about 25 minutes. And after that, we'll have about 30 minutes for a Q&A session. So please, if you have any questions during the webinar, please submit them via the Facebook Live event, and we'll go through those and choose some at the end of the presentations. Before we start, I'd like to introduce to you our president and founder of the SpaceRenaissance Initiative, and the reason that we are here today, Adriano Autino.
Okay, hello everybody. I'm very happy to be here, to have you here in this webinar on Mars. I just would like to say a few words just for greeting and for noticing to you that the Congress, the Third World Congress of the SpaceRenaissance is going ahead. We are holding several webinars, more or less 1 per month before June. And in June, at the end of June, from 26 to 30, we will hold our Congress that is titled the Civilian Space Development. So first of all, I invite everybody to register to the Congress and possibly to present, to submit their papers, your papers or abstracts for papers, presentations. Just go to the website 2021 SpaceRenaissance.space and you will see everything, the call for papers and everything. The other call, of course, is all of us to join the SpaceRenaissance crew, because everything we are doing is thanks to our members. So we make all of this, including Zoom professional licenses and websites and everything, thanks to our members. So one more member is very much important for us. 10 members are wonderful. 100 members would be a holiday, a party that
for sure.
we make online. So just 2 words of introduction for this fantastic webinar of today is that we at SpaceRenaissance think that we should have a space expansion, an expansion of civilization into space, a global expansion from Earth orbit to the moon and cislunar space to Mars, to the asteroid belts and beyond. And since today we will be speaking about Mars, we think Mars is the most important place in at the limitation of the internal solar system. Mars is an outpost to using the resources of the immense resources of the asteroid belt and beyond. So we see Mars as a logistic pole, a place where we have to stock our raw materials mined in the asteroids and maybe to process the materials there and so on. So I know what I'm saying is more or less, I think, the title of the Bruce Mackenzie presentation, that is Mars, the gateway to the solar system. And I think we have many different, and thanks God, we have many different points of view about space colonization and the expansion of civilization into space. But I think all of these points of view are synergical and can be key to develop a true space renaissance. So, okay, so this is my welcome to this webinar, and let's go ahead. Thank you very much.
Thanks, Adriano. My co-host today is Jerry Stone. He is a fellow of the British Interplanetary Society and a founder of Spaceflight UK. He is a freelance space presenter and author and an acknowledged expert on various aspects of space exploration. Jerry has given presentations on space across the UK and abroad for over 50 years, including countless conferences, events, webinars, and television and radio interviews. He's been described as one of the leading speakers on space exploration. And in 2013, he set up the Space Project at the British Interplanetary Society to update the Island 1 concept in the 1970s. And today he's going to be presenting on a development from this project titled Island 0, First Steps in Space Habitat Construction. Thank you, Jerry, and welcome.
Thank you very much, Shaun. And hello, good morning, good evening, wherever you are around the world. So I run Spaceflight UK, and I've been interested in space since I was knee-high to a lunar module. I want to talk to you about something which developed out of a project begun by Gerard O'Neill. He was a at Princeton University, and he posed a question to a new intake of students. He asked them, is a planetary surface the best place for an expanding technological civilization? I mean, obviously you'd think, well, you need gravity and other things, but the students went off, did some research, and the answer they came back with was no, it isn't. Because wherever you are, on the moon or Mars or anywhere else, if you have gravity, it means you have to fight against gravity in getting there. And also, if you then want to leave that place to go off anywhere else. The other main thing was that on any planetary surface, you lose the sun for 50% of the time, whereas out in free space, you can turn that sunlight into electricity to power everything. And you can also focus it to get 5,000 degrees to process all the materials. And so what they came up with was a different place known as L5. So if this is the Earth and that's the moon and there's its orbit around the Earth, then if you draw a line through them at a point between the Earth and the moon, you would expect that point to move ahead of the moon, and this other point, L2, to slow down behind the moon. But in fact, at these 2 points, the gravitational forces balance and they will stay in the same relative positions. There's also another point, L3, over the other side, not a lot of use. But these 3 points are unstable. Move away from those points, you'll continue to move away. But there are 2 others, 60 degrees ahead of the moon and 60 degrees behind it. And these are stable. If you start to move away, the combined gravitational forces will pull you back. So it's proposed that a space habitat be constructed at L5. And this was a design that came up. In fact, there were various designs. This is based on a sphere, as you can see from the central structure there. And there's also design based on a torus, which is the main bit there, and cylinders. Here, twin cylinders counter-rotating. But if we stick with this, at a scale of 10,000 people, this was designated an Island 1 level. Sunlight's reflected to the interior, which is where the people live. You have towns, villages, places to work as well. We take earth plants, trees. We could take bees to make honey, but we can leave wasps behind so we can have our picnics and parties in safety. The agriculture will take place in separate rings, so you can have whatever climate you need to help grow the crops without wondering about what it's going to do for the poor inhabitants. And how's it all constructed? Because lifting material off the Earth is very expensive. But fortunately, the moon can provide all we'll need. And the moon has two great advantages, apart from the availability of materials, which is there's no atmosphere. And during the lunar day, you have uninterrupted solar power, uninterrupted in that there's no clouds on the moon. So you can run an electromagnetic launcher and fire off the materials off to the construction point. And we know from the Apollo missions what lunar soil and rocks are made of, so that we can break it down and get oxygen to breathe, silicon for windows, iron, aluminium, magnesium for construction, and other things like titanium. So this was the idea behind this Island 1. But there were two deliberate limitations on the project. It had to cost no more than Apollo. So nobody could say, well, it's a nice idea, but we can't afford it. And it also had to be restricted to the technology available at the time. So nobody could say, well, it's a nice idea, but it depends on this, this, and this that we haven't invented yet. Well, it struck me a few years ago that being limited to 1970s technology had deliberately dated the project. At the time I was thinking of this, it was now 40 years on from there. And we had all kinds of new developments in technology, in materials. We had new alloys, we had new materials that didn't exist back in the 70s. And our computing power was many orders of magnitude beyond what it was back then. And it struck me that if we were to start this today, we could do it more efficiently and more cheaply than we could have back then. So I set up at the British Interplanetary Society the Space Project. That's Study Project Advancing Colony Engineering. So that's your introduction to my sense of humor. And one of the things that I asked the group of volunteers was, it's assumed in all of these designs that the structures will rotate to provide a simulated 1G environment. Do we actually need 1G? Suppose they rotated slow and produced 0.9G or even less. There would be less stress on the structure, so we wouldn't need as much material, and also less stress on the inhabitants, on their cardiovascular, their muscles, their skeletons. So they would live longer over a long period of time. They would grow slightly taller. We'd have to take that into account in the architecture. But the question then becomes, at what point does lowering the gravity become a problem rather than an advantage? And the answer to that, as they would say on QI, is nobody knows, because we've never done it. We've lived under 1/6 G on the moon for 3 days at the most. We've lived in weightlessness conditions for considerably longer, and as a result, staff on the ISS have to exercise for 2 hours every single day, but nothing in between. So suppose we could have something that would allow us to test this out. Not only that, of course, when we get round to actually building one of these structures, you don't start off by building the main structure. You need to have the assembly plants. Before that, you need to have the materials processing plants that will take the lunar material and extract the various ores and turn it into beams, girders, panels, windows, and so forth. And that's going to need people on site. And it would be best if they weren't living in full weightlessness all the time. So we came up with the idea of a smaller structure. So I've said that this sphere with 10,000 people was classified as Island 1. There were designs for 100,000 people habitats, Island 2, and the big level, the big cylinders, which could hold millions, were classed as Island 3. So we went the other way, and what we came up with was what we've called Island 0, based on units like this, 4.8 meters in diameter by 15 meters long, but not rigid like the units on the International Space Station. These would be inflatable, much easier to produce, and they can be taken up in deflated, compressed versions and then assembled initially in Earth orbit, but then we do them in lunar orbit and in other places. So that would be the size compressed, and this is the outline of the Skylon payload bay. And you could fit 4 of these in there at a time. So you'd only need 2 launches and a 3rd launch for other materials to complete the whole thing. Now, originally, we assumed this would be the kind of layout we get, and you can see from the human scale figure down there of the size of all of this. So we're talking about this being 50 meters in diameter. But then I did some calculations, and depending on the radius of the unit and how fast it was spinning, this is what the G-force would be. So you get 1G, and you can see that for 50 meters diameter, 25 meters radius, you're hardly going to get anything, even spinning at 3 revolutions per minute. So we have to make it bigger. Even to get 0.7 G, it would have to rotate twice a minute and be 150 meters in radius. Our preference was to go out to 200 meters. And just under 2 RPM, it would give us 0.7 G. But to have a ring like this, 200 meters across, means it's not a low cost thing, which is another one of our desires. So what we did was turn the units round and expand them. So there's the 200 meter radius, because you don't need to have this actually filled in every place, although we would have a ring, a tube, I should say, around the outside, which would really be for safety. So the inside would be split into different levels. That's where the safety tube would connect around the outside. And rather than have ladders between each floor, we envisage a spiral staircase fitted around the inside of the wall. So that's the Destiny module on the ISS to scale. 8 of these modules would actually give considerably more room than on the pressurized units on the ISS at the moment, but at a fraction of the cost. So here's a visualization of an Island 0 in Earth orbit. So there's the main unit. So the advantage of this is that if this is where the workers are sleeping, they're sleeping under gravity or simulated gravity, which is much better for their health. and they can still go up to the central hub to fly from there to the nearby construction and processing units. And we envisaged, as I said, one of these in Earth orbit for test purposes, the next one being constructed in orbit around the moon, and then at L5 points. But beyond that, we can see these usefully in orbit around Mars, perhaps attached as units not to an inflatable hub, but perhaps to Phobos, using that as the central hub. And it also then means people are immediately on hand to process material from Phobos and to break it down and to use it. So within our short period, I have to pretty much stop there, but I do want to say that this is the logo of the space project. And we also have a slogan courtesy of Blade Runner. So that's the vision of Gerard O'Neill, which we have slightly brought up to date, and we think has great advantages for all kinds of work to be carried on around the solar system. Thank you very much. If you want to contact me, please do so. Now, we're going to have questions for all of the panelists at the end of the session. Do submit questions through the chat on Zoom whilst you listen to and watch the other presentations. Our next speaker is Dr. Susan Jewell, the founder of the Moon Mars Astronaut Academy and Research Science. And she's currently preparing to build the first ever Mars analog settlement in the Mojave Desert. She's an expert in space health and safety and trains astronaut students of all ages from all over the world. She has deployed many missions to the Mojave Desert under MMARS, and this includes pioneering Space Medics training program and high-fidelity analog astronaut missions to Nepal, and plans for deployment to Everest Base Camp in 2021. Susan will be presenting on building the MMARS base and training analog astronauts to become future settlers on Mars and the Moon. Over to you, Susan.
Thank you so much, Jerry. Oh, excuse me. And wow, a frog in my throat. And thank you so much for inviting me to present the work that my team and I have been doing since 2014. Would you believe time flies, literally? So I am going to share my screen and also my slides. So please let me know if you, okay, all right. Oops, that's not the slide. What's happened there? Okay, let me start again. Where is my PowerPoint slide? Okay, do you see my screen,
That's
my
it.
slides?
That's up. We can see and hear you.
Thank you, Susan.
Okay, hopefully this is the right one because I corrected it like 10 minutes ago. But anyway, with that said, I know I have a certain amount of time, so I don't want to either, you know, I'll just improv if the slide's not correct. But thank you so much. Yes, I'm Dame Commander Dr. Jewell, and I have been working in the field of astronautics, specifically in space medicine and exponential technology for the last, well, 15 years or so. And recently, we have bought a piece of land in the Mojave Desert in California, United States, and we are developing and pioneering the first Martian lunar MMARSBase settlement that would eventually, hopefully by the end of 2022, we'll be able to house and train over 1,000 of our graduates under MMARS, where they'll live for long duration, up to 1 year to 3 years in full isolation confinement, and to be able also to test not only the architectural challenges of actually building a settlement on Moon and Mars eventually, obviously. This is going to be a new paradigm change in how we are also going to support the human health and safety under these conditions. So yes, this is a simulation analog vision, but we have also since 2014 have deployed smaller crew missions around here in Mojave, but also in austere environments, and to be able to develop and test technologies as well as human factors, right? So this is kind of what the vision of MMARS is. At the same time, we're a research institute, so we also look at deploying and testing, validating technologies that will support humans to not only thrive, survive, but thrive in austere environments of space on a planetary surface, but also, and this is very important for me and what I want to convey to the audience, is that we use space to innovate. We use space as a place to think out of the box, to solve huge major problems, because space is hard, right? To allow us to apply those new developments, new ideas, technology, procedures to improve life on Earth. That is the strongest connection, and that is ultimately the vision of what I want to do and what MMARS is about. So with that said, okay, why is it not going to the next slide? Okay, we had tested this, so I'm gonna have to stop sharing again and start again. So sorry. Why is this? Okay, so, all right, let me just apologize. It's, you know, Zoom technical. All right, let me try to share again my PowerPoint slide. All right, okay, this is the right one. Okay, let's start from the beginning. Do you see it?
Yes.
Yep.
Yes. All right. Okay, so, and I borrowed this beautiful picture. This is an artistic depiction of a future vision of a Mars colony. It could be, you know, let's not just say Mars, just say Moon, Mars, or any celestial body that humans can inhabit, right, on a planetary surface. But I love this picture because it gives you an imaginary vision of what we are trying to develop, create for us to become multiplanetary species, right? But in this picture, what do you think, besides the beautiful picture of the city there, is it's the human in this picture. It's the astronaut in this picture. Because yes, we are sending robots, and it'll be nice, your robots testing the environment, you know, looking at the capabilities, looking at the geographic terrain, looking at all these technology. But it's really what I'm interested in is, how do we build, how do we enhance the human capabilities, and specifically the health and safety of humans living in very dangerous extreme environments in space, on a planetary surface, or here in austere environments on Earth. That's what I am fascinated about. That's really what I want to do, right? It's the human factor. So every time you have humans in the loop, you better take care of them. And that is what we are trying to do as well. And then also integrate them into the paradigm. So building the architectural you know, city or the settlement. How do humans work with the architectural physical environment, the psychological aspects of that environment, the physiological aspects of that? These are huge challenges. So this is a beautiful picture, and it's the imagination. I love that. But however, what we're doing is, this is another picture. And what is this picture? This is a real picture of a sunset here on Mojave Desert, where we are building the MMARSBase. This literally is a real picture of a sunset. Look how magnificent that is, right? And this is something that I feel that, you know, it's using the imagination, but now bring it into reality and bring it into a practical, you know, opportunity for us to test this vision of that beautiful artistic, you know, rendering of the future vision, but we're actually doing it. So here is a real picture of a sunset, how magnificent that is, here in the Mojave Desert, where we're building our Mars base camp, or Mars base, not a base camp, but it's a Mars base, because it's going to be a settlement. And here's a picture of it during the daylight. And we are actually deploying now our analog crews here in the Mojave, and we reopened because of COVID, you know, in August, and now we're going to actually deploy missions here at our base, Mars base, every month starting in July. And these are called low fidelity missions. So when I say low fidelity, I mean it is not risky to life and death, right? We do, and in a minute, I'll show you pictures of us being the first organization actually deploy full immersion missions to austere environments in Nepal. And as Jared said, we are going to go to every space camp, Atacama Desert, Antarctica, the Arctic, later in this year and 2022. But the idea of the fidelities is because we want to really test the 3 Ps, and that is what 3P stands for: the physical aspect, the challenges, the psychological, the human factors, and the last piece, the physiological challenges of humans living in these environments and in full isolation confinement. And we all have experienced, because of COVID-19, some aspects and the challenges of living in isolation and confinement. We've all around the world, for the first time, actually really kind of, to a certain degree, understand what it is to live in isolation confinement. And so under these analog missions, I think this is an important factor of the human factors and the technology to able to solve some of these challenges of living in these isolated, confined environments for long duration of time. So, you know, astronauts, they're on their way to go into space, you know, in a spaceship that's confined, or, you know, the first settlers on the moon of Mars in a settlement or a base camp, they're going to be living constantly in isolation, confinement together. So not only that, you know, here's a picture of us pioneering the first station to station missions of analog crews. So here's what we mean by station to station is because we're looking at collaboration, communication issues on the same planetary surface, or even eventually different planets on the moon or Mars, and how do they collaborate together? So we did this in the Utah Desert with the Mars Desert Research Station, the MDRS, and we actually deployed. And what's so unique about our training facilities that since 2017, we've actually developed the first mobile portable base camp. So we were able to deploy our mobile portable base camp here about a mile away from MDRS. And we had 2 crews working together under this and it was in December of last year. Not last year, it was 2019. Whoa, times fly. And you could see that it was very extremely cold. And the night after we took this picture, the snow fell and it was like 3 feet of snow. So the crews were working 3 feet of snow, minus 12 degrees. And it was really, really challenging, both from the human factors, but also the technology that we were working on. So here I wanted to show you that when you come into our missions, we actually train you in different activities. It's a trained curriculum. So you're not coming in just like space camp. It's not space camp because we actually have career professionals coming in. And just giving an example of all the different training that you engage in. A lot of it is focused on exponential technologies. These are novel frontier technologies that will, enable humanity to actually thrive in space, right? So we do a lot of this technology testing, but here you could see all the way from lots of what we call EVA, extravehicular activities, search and rescue. We do geological terrain scouting. We also actually see the swimming pool there. we actually do underwater EVAs or underwater training, search and rescue underwater, using our also technology like virtual reality, where you could see here, oh, sorry, what happened there? Yeah, so here you could see the astronaut actually in the swimming pool wearing you know, the suit, but also the waterproof VR goggles. So they're able to actually experience, you know, virtually in a simulation what it is to be in space, or to work, you know, in space, but obviously through the virtual reality, and to do EVAs, search and rescue, triaging. But what's so unique as well, what we're doing is we're very focused on the commercial space and training commercial analog astronauts to eventually become the commercial astronaut corps. So the idea is, you know, yes, we have NASA, ESA, and they pioneer, you know, that the astronauts, they're living in low Earth orbit, they went to the moon, and they're trying to figure out how to take humans to Mars. But now the onboarding of the commercial space sector is what we're heavily involved in. So with SpaceX and Elon Musk, with his vision of building, you know, the Mars city on Mars, and then Jeff Bezos taking, you know, wanting to take humans permanently to the moon and building the moon base. This is what we're interested in the commercial sector. Why are we doing this? It's because we're really, I'm very much an advocate of, you know, trying to open the opportunities to anybody. Doesn't matter where you're from, what's your background, but if you're interested in going into space or building the technology to support humans to thrive in space, this is what we want to offer you, right? To be able to now finally, to be able to give you that opportunity and pathway, which prior to the onboarding commercial space, it was very limited. And remember, I, you know, actually at 7 years old, watched Neil Armstrong step on the moon. And 51 years later, you know, finally, I could see a portal opening for commercial space where anybody can be involved and literally have the possibility to go into space. So here, I just want to show you the timeline. There's our portable base camp that we've deployed since 2017 to all these different, you know, smaller crew missions around the world and here in Mojave. And then this is the Mars base. These big, huge geodesic domes connected by tunnels is what we're actually developing here in the Mojave. That will eventually house up to over 1,000 of our graduates, but they won't live there for long periods of time. And we'll also look at, you know, architecture. How do you build the architecture? How do you build the space clinic? Because obviously there is going to be accidents, and, you know, and that's what I'm interested in as well, being able to pioneer, you know, the health and safety, but space medicine is my passion. How do you keep the astronauts or the crew alive, especially if there's a large, you know, group, a large community, and how do you do mitigation countermeasures in, you know, being able to preventative health, integrative health. So here is another organization that I'm working with, part of the X Prize, is we're building the first, you know, humanoid telepresence avatar robot that is able to allow technology like spatial computing, AI, using haptics, and be able to then transport them as an avatar or using crew from the, here is showing you the medical way, the medical expert using telepresence avatar, but it could be anybody, it could be a tele engineer, could be a tele, you know, janitor, whatever it is, right, that would be able to support the crew remotely and come in. So here, we're actually, over the last few years, have tested the technology, and this is an actual crew. In our, this is of course an early prototype, our space clinic using this dome tent, and were able to test the technology using the robotic arm. This robotic arm, by the way, is all 3D printed, and we actually had the person about in Las Vegas, here is Mojave, in Las Vegas, 200 miles away, coming in as a telepresence avatar and be able to help the crew to do tele-anesthesia and tele-surgery. So this is something that we're innovating and bringing in to be able to help the crews on site to use technology, right? The integration, convergence of novel technology to be able to support the crew from a medical standpoint, from, you know, if there was an injury, how do they then conduct intervention like teleanesthesia to do surgery. And this is one way that we can envision happening. And this is the future of healthcare medicine as well, not only for space, but here on Earth. So, oops, let's go there. And here, just giving you some examples of a lot of technologies that we are integrating and testing when you come into our mission. And up there in the upper left is the first deployment of an analog mission to Nepal. This was at 10,000 feet, and we actually went to 15. We're going to Everest, and this is our space medics training. So now we're very focused on developing the technology, but also like, how do you keep, how do you train the crew that are non-medical to be able to conduct medical interventions when there's a life and death in, situation. So we actually look at, training them, not only the medical, protocols. So medical triaging, how do you actually train them to do medical, I can hear some noise in the background, medical triaging during isolation confinement in these very austere environments. And I'm going to say that in these austere environments, the reason why we go to these very dangerous, very risky environments, because we want, especially Nepal at high altitude, because it's the closest analog that you can get of humans on Earth to be closest to be in low Earth orbit in terms of the physiological and the medical standpoint, because people that deploy to high fidelity, to mountaineering, to Everest summit, is that they actually succumb, and it could be a death-threatening situation, medical situation, what we call high altitude mountain sickness. So we're looking at that, and then we are looking at developing technology for, to be able to use the technology to support them. And then so this is an example of a slide of a lot of technologies, using, for example, the UAV to do search and rescue, using down there in the bottom right is using space, for example, first responder, like, for example, CPR, and how to do triaging using this technology. Here is just another, when you come in, we do, R&D, and these are some of the projects that you engage in and that we bring into our mission. So, for example, using 3D printing as a technology platform, we're able to, be able to print the medical tools, the devices, then be able to integrate it into our medical, protocols and train the crews how to use them. And in the middle, actually, during the last 3 years, we've actually developed the first portable solar powered 3D printer laser cutter, and we test that in our environments. And if you're interested in knowing more, you can reach out to me. Last, also, we're very much focused on specialization training. So not only coming in to train in as an analog astronaut, we also have curated specialization training, including, because remember, we're very focused on commercial space, is that we actually have an entrepreneurial track and able to allow you to come in, use our missions as a laboratory in real environment, and be able to test your technology or your concept and be able to validate it and build a prototype, rapid prototyping, and MVP, and then maybe go on the entrepreneurial track, which we are very well versed with, to get funding and be a captain of your spaceship. Basically, that old adage of captain of your space, of your ship is, you are the one to develop your destiny, right? Your own journey. So if you're an entrepreneur, this is something we're very heavily involved in. So here, just really want to show you other aspects of when you come in to MMARS. It's not about just training. It's also about, and supporting you on your career path, as well as, if you're interested in the academic sector, we allow you to come in to work in our projects and also present and co-author manuscripts and so on and so forth. So it's many opportunities, and that's really what we're interested in. And finally, here is our virtual training that online virtual training. So this opens up the ability for everyone anywhere if you can't person for training, is that you can come in virtually on our virtual online. And later, for the VR AR, we can come in as a multiplayer and be able to learn how to, to work in a virtual cell and be able to learn a lot of the protocols and the countermeasures that we've developed. So with that said, oops, I think we are done, but I'm not sure why I can't move forward. Oops. Okay, I see why. All right, and so I'm just going to end here because I think my power is going to die. I'm here. Thank you so much. If you really want to, if you're interested in MMARS, please reach out. We are training superheroes with Dare to Dream, and this is my contact in MMARS. Thank you so much for listening.
Thank you, Susan. That was absolutely amazing. And we're very grateful that you were able to join us today and share all that the brilliant information with us and the exciting research that you're doing there. Our next speaker is Daniel Cottitta. Daniel is a passionate aviation and aerospace enthusiast. He's also an entrepreneur. He's a co-founder of Ripple Aerospace and United Frontiers Incorporated. An expert in rocket science and orbital debris, Daniel has a particular interest and expertise in ocean-launched vehicles and believes these will take us to Mars. So Daniel today will be presenting on heavy lift, advanced materials, and hydrogen, technologies that will propel humanity forward beyond the moon.
God, look at that cheesy face of mine. I'm not gonna lie. There will be personal commentary along the way. But good morning, guys. Good afternoon. Also, if you're on the other side of the world, I'm Daniel. I'm a co-founder of present-day United Frontiers, and we're presenting this presentation because a lot of things have popped up in the last 3 years alone that have really highlighted that, like, we're on a precipice, and a couple of new things are kind of under the radar or have been known on a more terrestrial level technology innovation, but have more potential in space now than they would have years ago due to either lack of technological progression or just not enough information and academic work completed to really present those works forward. So let me get the screen going. It says I could view my presentation. Oh, would you look at that? You see, I haven't really done Zoom myself, but we're going to get this presentation going. Here we are. Heavy lift, advanced materials, and hydrogen. At the time of building this presentation, I was inspirational in what I was and motivated in what I was writing, but I didn't have any real quotes, so I let my stomach speak for me. So I have no quote, just pizza. As a co-founder and a leading expert in ocean launch vehicles and space systems development and research, my existence to this world is well-rounded, and I have studied the sea, the rocket, and the machine god. For all that I know, I just might be Truax incarnate and not know it yet, because the attraction to these rockets and the resulting imagination to these vehicles is unbounded, and to the point where being able to leave aviation and co-found two companies to get and push that research forward again, resurrect this technology, and that endeavor and that risk was not unfounded. Being awarded grants in launch vehicle technology development for sea launch rocketry, doing successful maritime operations with test structures and ballast tanks, and getting it all towed by a boat, and getting approval from the FAA and the harbor masters and the city council, and making it all work. This work's been the work itself, and the information is also well-rounded and well-versed, being presented at the Mars Society, New Worlds, Small Satellite, and Disrupt Space, and presented plenty of times at the Space Symposium, hosted by the Space Foundation. I had the honor 2 years ago of being able to be on a panel for the University of Houston's SISCA Space Architecture Program for 2018 master theses that were being presented, and had the privilege of signing off on one regarding not so much sea launch vehicle technology at that point, but launch vehicles in general. And I was thoroughly impressed by that master's grad's work, and I do hope to participate more in the future with that university, either with the company and or myself. As we go on, our future within the solar system. The only thing I really agree with Jeff Bezos on is the ability to turn Earth into a sanctuary world and taking all heavy manufacturing off world and the populace with it that will sustain it, so that we can have a world that won't be destroyed by climate change and our own human intervention at this point. But that's more of a visionary perspective. But it does tie into that passion, my passion for space flight, and being able to, and again, my foothold, or my personal going in foothold for this technology is to bring sea launch forward, pushing boundaries of the human anatomy, lifestyle, economics with deep space exploration and settlement on advancing fronts. Reducing risk of travel between those 2 points over time. I mean, SpaceX is already proving that point forward by they have intent to launch over hundreds of starships before they ever put the first person in one. Contingency of resources and safety through ISRU and established cyclers, moving people, supplies, equipment. It's more than just rockets, but the rockets are the doer. But these in-space systems and processes are the enabler to sustain human settlement beyond the moon, Mars, and asteroids. Material innovations and manufacturing that incentivize exploration of all classes of asteroids, and we'll touch on that today later in the presentation. And last but not least, closing the gap on distances between between planets and moons, reaching Ceres, the Jovian system, to manageable lengths that we see here on Earth. So, as we've known for the longest time, it takes 6 to 8 months with current technology to go to Mars, and hopefully in the coming decades that we will see the same lengths of time be used to get to Jupiter, as opposed to the 2 years or 3 years to get between Jupiter and Saturn. These vast distances must be closed if we're to see ourselves advance further into the solar system. As we proceed forward, the emphasis of super heavy reusable ocean rockets is the competitive payload volumes and an ability to maximize your hardware that's being sent into space. I have a couple of diagrams shown. One was the United Frontiers Mariner rocket system, and we have a couple of other graphical examples of rockets in a shipyard manufacturing environment, built in mass. And one notable example constructed and designed by NASA was the Leviathan launch vehicle. And that was designed, it was kind of like a early 21st century resurrection of Truax's attempt at Truax's work. Robert Truax is the innovator and mastermind behind sea launch rocketry in the 1960s, proving all of its aspects and technological requirements forward via Aerojet and on his own through Truax Engineering Enterprises. The Leviathan was meant to lift it's about to be, lifting Saturn V size payloads, but also being a reusable launch vehicle. And again, a reusable launch vehicle is something that Truax conceptualized and proved forward the physics on paper and graphical representation that it was possible that sea launch rockets can be launched and recovered from the ocean in the same manner with the same infrastructure, nothing proprietary essentially. These and again, sea launch rocketry uses ports and established logistics hubs and hardware to be produced and launched. So it's got a lot of potential still, despite all these other innovations being presented and publicly released by Rocket Lab, SpaceX, Blue Origin. This is just some diamond in the rough that we're going to pull out soon enough. The bread's has already been kneaded. We're about to put this innovation into the oven, start baking. Here's one example advantage. Two example advantages is a reduction in ground support infrastructure and utilizing existing assets in the commercial maritime industry to build and launch any vehicle of scale. Seen here, it was just an example of part of a shipyard in Philadelphia, and they have machines that are able to move and construct, again, substructures for building Panamax container ships in excess of 20,000 tons a piece. And that kind of already shows the scale of potential in using the same manufacturing method to build launch vehicles. As well, once in the ocean, from an operational perspective, you do not need several dozen acres of land and thousands of tons of concrete to make a super heavy vehicle rated launch pad. The ocean is your launch pad, and all that you need to do is get the fuel and the boat to tow your vehicle via a ballast tank to the desired launch point, safely away from people and assets. And that's a wonderful thing. This is probably one of the safest approaches, and that's why I'm still biasly convinced that this is still one of the safest approaches to commercial space flight and our ability to reach the stars in a timely manner. One other thing that's been touched upon, again, last 2 years, is post-launch potential architecture. Now, it's not so much, it just wasn't common knowledge until NASA started putting more money into it and more of the mainstream media started harking on it, but that the ability to use reusable spent rocket stages and even payload fairings to some extent, and reconstructing them into habitable space station habitats for human settlement and or presence for extended periods of time will be essential to reducing the cost of larger spacecraft production or space infrastructure production, again, depending on the niche of the mission, and will reduce the cost overhead to doing these lengthy endeavors for long-term gains from a commercial perspective, as well as scientific. We want to be able to. It kind of feels like it almost feels like the rockets are kind of like the buffalo of our time. The buffalo, and by Native Americans, they used every single piece of the buffalo after they killed it. It's the same deal with the rocket. After the rocket's been spent in space, we're now attempting to really reuse every single piece of that rocket to its effectiveness, so that we're not expending it in orbit, and that's a greater space debris problem and a whole discussion otherwise. Missions to return. Now this is something crazy. I'm going to go on a small commentary, but this image was found on the internet first, like all things these days. But what really stood out was that this image was a graphical representation by Aerojet, NASA, to be launched of a prefabricated Mars base to be launched by a Sea Dragon. And that was found, again, this was found in real world at the Smithsonian Aerospace Archives in DC. And that's when I realized that they weren't kidding around back then on their ambitions, and how much money they had really spent into the Sea Dragon program through Aerojet was more than annotated online. This prefabricated base, for example, was launched via the Sea Dragon architecture per the concept of operations in the paper that they had discussed this idea, again, on a greater ambition to post-Apollo planning, that it was going to be launched by this ability to launch a prefabricated base by a Sea Dragon, which couldn't be done with a Saturn V, let alone anything else, via a land-based launched rocket architecture. With an approximate lift mass of 750 metric tons, results in a prefabricated base, seen here, resulting with a useful tonnage of 180 metric tons and more, successfully reaching to the surface of Mars. All set, ready to go for human habitation and long-term living on the red planet. So that was that real indication that like this rocket was really delivering on that visionary promise to make the travel to space a near zero death experience and extended living a near zero death experience. And this was from 60 years ago. So again, personally, with team and effort and colleagues and peers, we have that ambition to bring this back by any means necessary. Additional results of super heavy reusable vehicles in general results in supply ships to orbit to maintain a high cadence of goods of quantity and or quality that couldn't be done via ISRU. The ability to create cycler belts and cycler vehicles that are transit nodes to planets, moons, and Lagrange points. Heavy machinery and or manufacturing to superstructure engineering, tethers, space elevators, and the fourth, can now be economically feasible through repetitive super heavy launch vehicle architectures. So it's inevitable. We're all seeing small sat vehicles now, but as we've seen, a lot of these small sat vehicle companies have had ambitions for the longest time to make a bigger vehicle. On the next part, you're wondering, how do we power all this stuff in space, these bases, these stations, these manufacturing envisions, Dan? Like, come on, get real here. All right, so we're talking about hydrogen. That hydrogen is making its moves from an industry perspective, has been successfully making its moves here on Earth because we are in a climate crisis, and the hydrogen is the next best thing forward to powering our world forward. Same in space. It's the most abundant element in the universe, and it's also very stable in a gaseous state. Very high power output, 33 kilowatts per kilogram, and I'll show you in those examples forward. These, for example, industrial vehicles like this mining excavator can be powered for several days on just several thousand metric tons of gaseous hydrogen and gaseous oxygen. Again, stable versions of these elements in a compartmentalized form can power a vehicle of this size for several days, whereas on Earth with just a fossil fuel can only be run for 12 hours. This results in vehicles of this size and or mass to be operated for days on end, maximizing its effectiveness for human settlers and manufacturing endeavors off-world. A second example is industrial machining equipment. So my example here was an orbital space manufacturing facility, and for simpler purposes, let's say that same power system is also powering the space stations and manufacturing equipment. The same type, you can now have something that as in 160 kilowatt per day per hour use, total of almost 3,400 kilowatts over a 20-hour manufacturing cycle. Again, that same power source allows for 76 days of manufacturing operation. And when supplemented with solar arrays to run non-manufacturing systems, this allows for a near constant supply, a near constant supply of power where needed to, again, run all those systems. And when integrated with an ISRU logistics network, whether it's things from the moon or an asteroid, we can get a stable fuel supply and keep these things running forward. My last bit will be a little cut short, that we have the potential as humans to make use of carbon type asteroids, which are of non-value asteroids, but we are actually of very high value asteroids in that they have the ability, we have the ability here on Earth to construct graphene and or graphite through artificial processes now, as well as activated carbon, which are needed for human in general, but activated carbon using for oxygen filtration systems and other composites here on Earth, and in coal type compounds, as well as a raw material can be broken down into usable carbon materials needed here on Earth, but then compounded as well off-world, and it results in the manufacturing of electronic components, thermal protection systems, hull reinforcement structures for ships, and heat sinks, or as well, and in a potential future, new carbon majority metal alloys, because these carbon asteroids are just filled to the brim with one or less than five compounded elements. And that we can make full use of these lower value asteroids to sustain a longer manufacturing sustainment on that particular body before having to go away from it. That's it for now. And one last note is that when going through the Smithsonian archives of Robert Chirax's work in sea launch rocketry, that he had presented forth in several video presentations what Sea Dragon was meant to be used for. And turns out he had been with Gerard K. O'Neill at least half a dozen times discussing how to use Sea Dragon for heavy lift heavy lift-based projects and programs for human settlement in space. And the O'Neill cylinder was one of Truax's leading examples of like what this launch vehicle can do, is make those types of superstructures cost effective. And that's it. That is all for now. I appreciate you guys listening, and look forward to hearing everybody else. Thank you.
Thank you very much, Dan. If you can stop your slide share, then mine should come back, I hope. Okay, let's...
Jerry, I can just start my slides if you want.
Okay, well, I just need to just transfer over to this anyway, because obviously I need to introduce you. Right, well, Bruce Mackenzie is a world expert in Mars settlement. He's been involved in the Mars Society virtually since its inception in the late 1990s, and as a founder of the Mars Foundation and leader of its core projects, Mars Homestead and the Hillside Settlement, which arguably remains the most detailed and advanced design study ever conducted of a permanent human settlement on Mars. He's also a founder of Marspedia and Mars University. And his presentation today is entitled Mars Gateway to the Solar System. So over to you, Bruce.
All right, thank you. So there we go. Okay. Yeah, I've borrowed some of this from another presentation about what you might export from Mars. I think that Mars is a good place to establish a first permanent settlement for several reasons, but it's not the in place. I very much believe in Jerry O'Neill's vision. I got the privilege of working with him briefly. And I think someday most of our descendants will be out among the asteroids somewhere in orbital settlements. So, anyway, I'm assuming, so I've done a lot of work designing Mars settlements, some just back of the envelope, some have been turned into papers and presentations. There's one of our designs in the upper right. I'm assuming that for the purpose of this presentation today, that we will have a widespread civilization throughout the solar system, but the resources of the solar system are uneven. You know, there are some asteroids that are almost pure iron with a little bit of nickel. There are some comets that are mostly volatiles, water. Luna, the Earth's moon, is rich in silicate rocks, and it has a very, you can do teleoperations from Earth very, very quickly. So there's an uneven distribution of resources, labor, and solar energy. So how might a future trade or exports from various areas take place? And in particular, can Mars actually export enough to get paid for and have a purpose, be able to get hard currency into Mars to export more things? I happen to think that there'll be a lot of work around Phobos and Deimos, the moons of Mars. And I will say later that I think a space elevator from Phobos is the key to all this. So, okay, trying to advance my slides. Okay, I always like to start with a couple of quick slides saying why civilization should go into space and actually bring life with us. It's for the benefit of our great-grandkids, broaden their horizons, the essentially unlimited resources of material and energy in the solar system, but also learning how to manage an ecosystem. If we can have thousands of independent space settlements, people will have to learn how to manage all the recycling, their air, water, and food. And those lessons might be applicable to the Earth someday. We may be able to avert a global catastrophe on Earth based on the ecological lessons we have learned. I can go backwards, but I can't go forwards. All right, so by the way, here are other images of space settlements inspired by Jerry O'Neill. There's enough resources in the asteroids to provide enough climate-controlled land that is something like 3,000 times the Earth's land area. So if we can get that first factory out there and then use that to build more space settlements, someday there'll be room for trillions of people living off the Earth. And that realization has changed my life. Okay, why start with Mars? Same reason. It's food, food, and food. Mars has water, easily accessible water, ice to grow food. It has easily accessible carbon and nitrogen. Nitrogen is needed for fertilizer. There's minor reasons to, the carbon's useful for polymers. Also, it is easier to establish a settlement on Mars than an asteroid because you can just run an air pump and get more air back in, more carbon dioxide, convert that to oxygen. On an asteroid with minimal gravity, every time you open an airlock, you lose air and water vapor. So Mars is a more forgiving place dealing with that. And going to Mars would also teach us interplanetary travel and manufacturing off Earth. If you notice that this is upper right is Elon Musk's SpaceX's proposed Mars city, watching a Starship take off. Some things that bug me are the really futuristic designs that would be hard to build. You see a dome here that is very, very large, tremendous stresses on the top of the dome. Tomorrow we have a deadline to turn in a paper, and this is a draft image from it. So if any of you want to help design Mars settlements, this particular one would be an open park, perhaps 100 meters wide. Think of a city park with a bunch of cables pulling down, so you don't have the incredible stress on a large dome. So let us know if you want to help either with management, website, or engineering for future projects. Address is info@marsfoundation.org. Okay, skipping right along. I don't think that there can be exports from most space settlements all the way back to Earth that would be economical. There's a few exceptions. We'll get some money for scientific exploration. I'm hoping that someday we can sell land and condominiums on the Mars and space settlements around the moon, and people will pay money to go travel to those, space cities and live there, purchase a condo, purchase food, and get a job. But it's really going to be trade between the space settlements and places to live is what's motivating me and others. There are proposals both by us and others for Mars settlements. I'm assuming that they will have manufacturing facilities. The top one is our hillside settlement. We think it can be built with 12 people and a lot of semi-automated equipment, and would take our original mass estimate was 250 tons of equipment delivered to Mars, could bootstrap the manufacturing and then build this. The keys are built with polymers and locally produced fiberglass. This slide is just for fun. I and others have proposed masonry architecture. For Mars, put enough dirt on the roof to hold it down. So there's just to show there's a variety of ways of building and living beyond the Earth. The Romans or Greeks could have built this, except for that little pressure door you see under the balcony back there. And just for fun, some software messed up Brian Versteg's image of a greenhouse for us, and I left it in the lower left as an inflatable greenhouse that has not yet been inflated. So the wonders of bad software is showing through. Okay, so space elevators. You can take, so space elevators would be very hard to drop down to the Earth because we don't have a material yet that is strong enough. People are working on it. I recommend ISEC, the International Space Elevator Consortium, for more information. But on Luna, the Earth's moon, or Mars, or the moons of Mars, you can use conventional material. The really high-strength fishing line, some of it is called Spectra 1000, Spectra 2000, could be used to drop a very thin cable down from Phobos, moon of Mars, toward the Earth's atmosphere. And you could launch a fairly slow rocket up above the atmosphere, doesn't have to have full orbital velocity, and catch the end of that space elevator, and then climb up it to Phobos. So this is a way that we can export anything from the surface of Mars. You might even be able to use some sort of magnetic launcher, railgun, spinning tether on the Pavonis Mons, which is a mountain on Mars near the equator. Lower right, I show a possible way of catching it. That diagram's about 30 years old. You basically use a big harpoon and catch a cable. Okay, so, and I think we can produce manufactured goods on Mars, package them in small enough rockets to be held on this space elevator, and export a lot of material, finished goods, and maybe even food from Mars up into low Mars orbit, assemble the small pieces into a whole spacecraft, and then send them up another space elevator pointing away from Mars, release them, and they can fly most anywhere in the solar system. So in the upper right is Mars and the various orbits. I think this is to scale. So that blue horizontal line represents a space elevator. The black dot is Phobos. You drop this fishing line down about 5,000 or 6,000 kilometers to near the Mars atmosphere, and then extend it up. And by climbing that upward elevator and letting go, you can escape from Mars. You can travel with no rocket fuel all the way to the Earth, or even to nearby asteroids. And I wish this was interactive. I wish I could see everybody's faces on Facebook so I could take questions, but sorry. So there's one more wild card I want to mention. There are people working on atmospheric scoops. It would be a spacecraft that could dip down into the atmosphere and collect gas. This was thought to be impossible because of the heating, but people are working on it. It might be possible for both the Earth, Mars, and some of the moons in the outer solar system that have atmospheres. So there's another wild card. It's if we can capture nitrogen from Earth, or carbon dioxide from Mars, or methane from a moon, this is a wild card. It'd be interesting to see how that affects the solar system-wide economy. Okay, the upper right is a beautiful image by Brian Versteg, I believe, mining an asteroid and building a very large space settlement, perhaps a kilometer across. The image in the, and I'm thinking that this mining equipment might be manufactured on Mars, lifted to Phobos, assembled, and then sent out to a bunch of asteroids. Interestingly, in the lower left, I believe this image is from the late 1970s, so that's more than 40 years old. And somebody has done an asteroid redirect mission 40 years ago, at least some artist did it, and they're assembling a solar power satellite. And there's that vernal sphere in the lower edge. So people have been thinking about this for a long time. The artist did not really recommend asteroid redirect, by the way. So here's a list of what we might export from Mars if we can get the launch cost cheap enough. Fuel, water, nitrogen for fertilizer or fertilizer, and methane and ammonia have additional uses. You could export ammonia to Luna and combine it with lunar oxygen to make water, because the ammonia is nitrogen and hydrogen, so you can make water by burning ammonia on the moon, and then you also have nitrogen as a breathing gas. I mentioned fertilizer, so let's go on. Oh, by the way, this image is a gas compressor and separator unit proposed by Case for Mars #2 conference. It predates Bob Zubrin's work back from 1988. And you can see the biconic entry shell on the left that I'm sure Shaun is very familiar with, because that's the basis for the proposed Mars analog HABs in Australia. There is plenty of water ice on Mars as close to the equator as 40 degrees north or south latitude. This was one of the earliest ones they discovered. They had a radar mapper in Mars orbit, and they discovered a half a kilometer of some material. It's shown on the radar cross section is on the left. So there's half a kilometer of either ice or something else that is transparent to radar. I like to joke, it could be styrofoam built by an ancient alien civilization. In either case, let's go there and find out what it is, and if it's ice, let's drink it. Oh, by the way, there's a stream right next to this ice deposit that might be a good source of sand and gravel and silt that could have industrial uses. Upper left is, those blue dots are some of the larger known water ice deposits on Mars. Upper right is a methane fuel production unit prototype that was built by high school kids in Dallas. So you don't need to be a rocket scientist to make rocket fuel. You just need to be a kid in oil country and know it's needed. The image in the bottom is mostly just a moon shot, but you could imagine assembling spacecraft in Mars orbit and sending them elsewhere throughout the outer solar system. Sorry to be so fast, but I think I've mentioned this. You can sell fuel in Mars orbit, and it's also when people or goods arrive at Mars, they might arrive with empty fuel tanks, and you want to fuel them up before they land on Mars. So you might have to export methane and oxygen from the Mars surface to Phobos in order to land with a Starship class rocket. Hey, I'm on time. Let's see. I think I mentioned everything here. Oh, all those volatiles. Oh, exporting all that methane and ammonia and water, and you can export them in graphite tanks. So you launch a small graphite tank up to the elevator, lift it up, send it to Luna, and they will take the ammonia, breathe the nitrogen, drink the hydrogen as water, and then they can burn the graphite in their greenhouse, and they get extra carbon dioxide to grow more crops from burning the graphite or reusing it. Here's a fun thing that a lot of people haven't heard of. It's mostly just for fun. I'm throwing it in. Jeff Landis has figured out that you can have floating towns in the Venus atmosphere. If you're up where you have Earth sea level atmospheric pressure, it's reasonable temperature, you can fill a giant balloon with breathable air, nitrogen and oxygen, and that is a lifting gas. And then you build a house in the bottom of the balloon. So you can actually live in a short sleeve environment above the clouds of Venus. Well, they're going to need imports. I don't think there'll be a thriving civilization there, because I can't figure out how to export much of value from Venus. But you know, let's build these balloons somewhere in space and drop them down in the Venus atmosphere and have some scientific have a scientific base in the clouds. I mentioned graphite tanks, also steel might be slightly easier to make on Mars than many places, easier than on Luna. Mars has slightly more oxides in its soil than typical. So, just for scale, this fiberglass tank in the picture is 4 meters across. I'm recommending tanks, well, habitats for living 5 to 8 meters in diameter, so about that size. Okay, this is controversial, but I would like to investigate it more, especially if anybody wants to. Could Mars export food productively, economically, to elsewhere in the asteroids and even back to the Earth's moon? I think it might be possible. Mars has a lot of water, enough nitrogen, well, enough water, carbon dioxide. Those are basically the ingredients for food. I think it will be cheaper to live on Mars than in orbit for reasons I mentioned. So there might be quite an agricultural business, growing food on Mars, making freeze-dried pizzas or dehydrated and lifting them up and exporting them and selling them. I was joking with Shaun last night that we might even export food to sell in Hotel Luna, or the Luna gambling casino. Okay, I think that if it is economical to export food from Mars, it might be short-lived, because at some point there are going to be a lot of orbital greenhouses, and it'll be cheaper to grow food where there's 24-hour sunlight closer to where you want to eat it, except for the outer solar system. But if the space elevator works out, the Mars farmers might convert to an industry of building greenhouses and selling turnkey greenhouses throughout the solar system. And in the interest of time, I will skip. Just to say, anytime you want to launch a pre-made pressure shell from Earth or Mars, why don't you fill it with fuel and use that fuel on the way up? This was the original plan for Skylab. So launch all your structures wet, meaning full of fuel, if you can. The whole business, designing and building furnishings, furniture and kitchen utensils and exporting those. Other exports, you can make graphite tethers or graphene tethers on Mars and export those. Okay, let me stay on this slide for a minute. I believe that it will continue to be cheaper to live on the surface of Mars than in orbital settlements for a while. And there may be a business of workers on Mars teleoperate, and they control machines in Mars orbit to do the assembly. So even if the export of physical materials is expensive, we might be able to export the labor from the surface of Mars to Mars orbit through remote control. Okay, and of course, all this manufactured goods can expand its civilization on the Mars surface. So, and that is it. I think I'm actually ahead on time. So to summarize, we have uneven distribution of natural resources throughout the solar system, including energy and labor, and there's going to be quite a business of interplanetary or solar system-wide trade, exports, travel, and bulk shipments. Thank you. My email address is at the bottom. Feel free to contact me, and also both the Mars Foundation and the Mars University can use help in a number of ways, especially we'd like to restructure the management of the Mars Foundation and get more people involved in planning of various studies. So thank you very much. Back to Jerry, I believe. while I enjoy my dihydrogen monoxide, which is a chemical precursor of rocket fuel. You can decompose it into hydrogen and oxygen and burn it.
The dihydrogen monoxide. Yeah.
Yes, also known as hydrogen hydroxide. It's very dangerous.
Yeah, I know. I tell kids about it in school.
Yeah.
Okay. Right. If you can stop your screen share, Bruce.
Yeah. For future reference, I think you can override someone else's screen share.
It's not actually so easy.
I don't know how to get the full zoom back, so I.
No. If you just stop.
I found it. No, I didn't. I couldn't find the button. It had changed on me.
Oh, okay. Don't worry about it. Let's share. This should be coming up in a second. That is. Right, I have.
I believe the next speaker is Shaun Moss.
It is Shaun.
Shaun has written some books, lives in Australia, and has been active in Mars designs for decades.
Feels like decades.
That will do. Actually, I can see what's happened. I shall stop this because my keynote has it is unfortunately hidden. Yeah, Shaun has been extremely active in development of Mars on the theoretical side. Unfortunately, we have to say.
Shaun's a beast. He knows what he's talking about.
Well, that's basically the main thing that is a prerequisite for our speakers. You can see from his background, he's already out in space. So I think,
see, he already won the race here. Like we should just go home. He's already in space, you know. All right, sorry.
That's okay, because my keynote is closed anyway. So I'm just going to hand over to you, Shaun.
Thanks, Jerry. That's great. Thank you.
Take it away.
All right, let me share my screen.
And Shaun, try to get closer to the microphone.
Yeah, sure. Okay, so today I'm going to talk about settling the solar system, the best destinations beyond the moon. So these are some of the places that I think that we are most likely to settle over the next, let's say, few centuries. Very briefly about myself, I've been involved in the space community for over 20 years, mostly the Mars Society, but a few other groups as well. I wrote this book called the International Mars Research Station, which is a concept to develop a permanent human presence on Mars by getting a bunch of space agencies to work together. And I did a TEDx talk about this, and you can find any more information about this at MMARSBase.org. On social media, almost everywhere on Mossy2100. That's Twitter, Facebook, LinkedIn, YouTube, and Reddit. So I'm easy to get hold of. So of course, Mars is our favorite planet. And when we're talking about human settlement of the solar system, it's become more clear over the past, I guess, 10, 20 years that Mars is by far our best option. It is pretty close to Earth, so it only takes roughly 6 months, give or take, to reach Mars. The communications lag is not too bad. It ranges from about 3 to 21 minutes. So of course, a short travel time means lower cost and less exposure for the travelers to the radiation of interplanetary space and microgravity. Mars has multiple sources of renewable energy, which is a big plus. The solar power intensity is about half what we get on Earth, which is plenty. You also have wind power on Mars and potentially also geothermal energy. Mars has plenty of water. There's ice over virtually the entire surface of Mars. And it has a particularly good atmosphere, which is an abundant source of carbon, oxygen, and nitrogen. It serves to distribute heat around the planet. So on Mars, we don't get the extremes of temperature that we do on, for example, the Moon and Mercury and other airless bodies. It's useful for aerobraking and aerocapture, which reduces your fuel requirement when arriving at Mars. And it's transparent. It's the only world other than Earth in the solar system with a substantial transparent atmosphere. It means from the surface of Mars, you can see space, and from space, you can see the surface of Mars. This is an advantage that we don't have, for example, on Venus and Titan. The length of the day on Mars is just slightly longer than a day on Earth, which is a big plus. There would be significant psychological advantages to that. It would feel familiar. You would assume that it would be easier for people to adapt to living on Mars, and also it will be easier to adapt our crops to growing them on surface greenhouses. It has a familiar progression of seasons. Mars has an axial tilt almost the same as Earth's. The gravity is a bit of a two-edged sword. It's only 0.38 of 1 Earth G, which we don't know exactly what the effect this will be on the human body. We won't know until we actually do it, probably, or until we can simulate it. But we would expect there's probably going to be some muscle and bone loss among Martian settlers, which is not ideal. It might make it quite difficult for Martian settlers to return to Earth. However, on the plus side, it's a good level of gravity for EVA. If you are wearing a spacesuit, for example, that weighs 50 kilograms, which is about half what the Apollo spacesuits weighed, on Mars, it would feel like it only weighed 19 kilograms, which is reasonable. You could imagine spending several hours working on the Martian surface and wearing a load of that size. But if the gravity was much higher, it might be more difficult. It has 2 moons, which is something we can't say about other worlds that we're going to talk about. That represents 12 trillion tons of useful material already on orbit. So we've talked a lot today about building habitats in space. Certainly the largest cost involved in building space settlements in orbit is getting the material to site, because launch costs are still quite high. But at Mars, we already have all of this mass on orbit, and most of it's in Phobos, 90% of it's in Phobos. So we can use that material to build a space elevator, as Bruce was talking about, or we could use it to build orbital settlements, orbital hotels, space satellites, solar power satellites in Mars orbit. And we already have all that mass sitting there. It's made of magnesium and iron and nickel and oxygen and carbon, all useful stuff. Mars is very beautiful. As I said, you can see the stars from the surface. It has a nice terrain, which is reminiscent of, for example, Arizona or South Australia. And it may possibly be terraformable, meaning that we may be able to modify the environment of Mars over a period of time, such that it could support plants and animals on the surface, which is incredibly important for our future. It may actually be the planet where we can back up Terran life. So in the event of an extinction level event on Earth, there would be another place in the solar system where you could find humans and other Terran species. There are a few downsides. Probably the most serious one is its synodic period with Earth. We can only go to Mars every 26 months. It has actually the longest synodic period with Earth of any planet in the solar system. This means that when we send humans to Mars for exploratory missions, they're pretty much committed for quite a long period of time. It means the equipment has to last a long time. It means we need to consider spare parts and in situ fabrication and repair. The radiation is somewhat high. It's not ridiculous. We can still work on the surface of Mars, but in terms of settlement, it is likely that we will want to spend most of our time underground, probably ideally below at least several meters of regolith. And it's also pretty cold. It's about as cold as Antarctica at its coldest. So we need energy for heating. Now, the next destination that I expect that humans will want to settle beyond Mars is Mercury. And the main reason is that Mercury has some specific similarities to Mars and the Moon that we can exploit. So Mercury has virtually the same gravity as Mars. So you can imagine the difficulty that Earthers will have going to live and work on Mars, because their bodies will adapt to the Martian gravity, and it may make it quite difficult for them to return to Earth. But people who are already adapted to Mars would be able to go and live and work on Mercury and return to Mars without experiencing significant medical issues relating to low gravity. So what we might see in the future is quite a lot of travel and trade between Mercury and Mars due to this similarity in gravity, at least until we solve that issue. The axial tilt on Mercury is almost 0 degrees, just like the moon, which means we will probably colonize the poles, just like on the moon. That's where most of the solar power is. It has peaks of eternal light like the moon does, and it also has craters of perpetual darkness, which is where you find most of the water and other ices on Mercury. So we will have some experience on the moon colonizing the poles and accessing these ices in these permanently dark craters, and we can obviously leverage that experience as we go to Mercury. Mercury has a short synodic period with Earth. We can go there every 4 months, which is very useful for exploration and supporting a settlement. You can do 3 flights a year to Mercury. It's the closest planet to Earth on average, with a fairly low communications lag. And of course, being so close to the sun, you get abundant solar energy, 7 times the intensity that you get on Earth. Now that's also a problem because you get very high radiation on Mercury. You would almost certainly be living underground. There are extremes of temperature on Mercury because it is airless. And so again, you would want to be living underground at a temperature. The temperature under the ground on Mercury is somewhat more benign. And the main issue you'd be dealing with is the fact that surface structures and vehicles would suffer from thermal fatigue due to the continuous cycle of hot and cold. There's very little water and hydrogen. As I say, the water is concentrated in these permanently dark craters at the poles. So that's a problem. You would have reduced warning of solar particle events compared with Earth, and quite long nighttime periods. Now, the next planet I'm going to mention is Venus. Now, Venus is actually probably somewhere we won't be able to settle for quite some time. However, because it's so close to Earth, it's almost certain that we eventually will. We'll eventually figure it out. It is called Earth's twin because it's so close to the Earth in mass and size. It's the planet that comes closest to Earth, which means the trip times can be fairly short and the communications lag is fairly low. You have double the solar power at the top of the atmosphere compared with Earth. There are significant carbon, oxygen, nitrogen resources in the atmosphere, plus hydrogen and sulfur in the clouds. The gravity level is fairly similar to Earth's, which is healthy. Venus is somewhere where you could go and spend some time and probably return to Earth without significant gravity-related health problems. There's significant wind power, especially at altitude, and it may be terraformable. A lot of thinking has gone into how Venus might be terraformed, but it would be a significant project and much harder than Mars. It is extremely hot at the surface. That's the main issue over all of Venus, including the poles. And the atmospheric pressure at the surface is extremely high, 91 atmosphere. It's equal to being about 1 kilometer underwater. There's almost no water at all. It's extremely dry. Clouds and rain of sulfuric acid make the surface a very hostile place to inhabit. You have no solar power at the surface and very long nighttime periods. So this slide, basically Bruce already covered, but some thinking has gone into how we might build floating settlements above the clouds on Venus, because once you go up about 50 kilometers, you get a much more benign Earth-like environment, about 1 atmosphere pressure, 0 to 50 degrees Celsius. You still have plenty of atmosphere above you, which provides substantial radiation protection. There's lots of solar and wind power available to you above the clouds. You could mine the atmosphere. Your main challenges would be where to obtain metals, because it's probably not going to be possible to get them from the surface of Venus. Possibly acid corrosion if your habitats are excessively exposed to the clouds, and very high wind speeds, which would place significant stresses on those habitats. Now to the asteroid belt. This is the asteroid that I think will accommodate the most number of people in the future. It's called 16 Psyche. It's the largest metallic asteroid in the belt. It's believed to be almost entirely made from metal. Now, metallic asteroids are quite possibly the asteroids that will be the most colonized for two main reasons. One is that they can be spun. Because metal has a much higher tensile strength than rock or ice, you could dig out a habitat inside an asteroid, a metallic asteroid, and spin it to create artificial gravity, even Earth-level artificial gravity inside the asteroid habitat. And it wouldn't fly apart, whereas some of these other types of asteroids, carbonaceous and stony asteroids and icy ones, they wouldn't have the tensile strength to remain in one piece under the centripetal forces. So they're not so easy to spin. And Psyche is the largest, but there's an estimated on the order of 100,000 asteroids, metallic type asteroids in the belt with a radius of greater than 1 kilometer. The second reason why we are perhaps more likely to colonize M-type asteroids is because the metals are valuable. Not only is there an abundance of iron and nickel, but you also have gold and platinum group metals and other heavy metals which have a high value. Psyche, being the largest, has an estimated value at today's prices on the order of $10 quintillion. So this is a space settlement that can pay for itself. The settlers could excavate an asteroid, excavate a habitat inside the asteroid and sell the metal to pay for the construction. Now to the Jovian system. Jupiter has an abundance of moons. Most of them are in a retrograde orbit, quite distant from Jupiter, and these would be a useful source of resources. But the ones that we usually talk about when we talk about colonizing the Jovian system are the Galilean moons, which are closer in to Jupiter here, and these are quite large. They're all larger than 3,000 kilometers in diameter. Here they are. If you want some sense of scale, the moon, our moon, is roughly in between the size of Io and Europa, and Callisto is about the size of Mercury. And these go roughly from worst to best in terms of their potential for human settlement. Io experiences significant tidal forces, and it has over 400 active volcanoes and no water whatsoever. It's the driest object in the solar system and extremely high radiation environment. Europa and Ganymede also, there's some advantages there in terms of water. Europa is of particular scientific interest because water sometimes flows on the surface and it's considered a place where life might develop. However, these moons also are in a very high radiation environment. Callisto the radiation on Callisto is quite low. There's plenty of water, and it also, being the farthest Galilean moon from Jupiter, has the lowest delta V, so it's the cheapest to reach. Here's the problem. The main issue is radiation. Jupiter has an extremely large magnetic field. It's 20 times as strong as Earth's, and it produces this powerful magnetodisk around it. And Io, Europa, and Ganymede are all within this magnetodisk, whereas Callisto, which is nearly twice as far from Jupiter as Ganymede, is outside of it. So if you look at this table on the left here, we can see a comparison of radiation environments. If we look at the moon, for example, there's about 100 times as much radiation than there is on Earth. But Ganymede is about 100 times greater, again, 10,000 times more than you experience on Earth. And you just look at how much more there is on Europa and Io. But Callisto is comparatively benign. We wouldn't have to live underground on Callisto. We could build surface settlements. You would have access to plenty of ice. Callisto is about half made of ice, plenty of water and CO2 and nitrogen as well. There's possibly a subsurface ocean that could be tapped. Unfortunately, Callisto doesn't have renewable energy. There's no solar, wind, or geothermal energy. So you would be pretty reliant on nuclear power if you were going to build a settlement on Callisto. It is extremely cold. The gravity is quite low, even less than our moons. Now, finally, to the Saturnian system, which is an exciting prospects for colonization, Saturn has even more moons than Jupiter, including 7 major moons, the most of any giant planet. But these are completely dominated by Titan. It's the largest moon in the solar system that we could potentially colonize. It's the second largest moon after Ganymede. It's bigger than Mercury, and it is the most Earth-like moon in the solar system. It's the only moon with a significant atmosphere. The pressure at the surface of Titan is about 1.5 times what it is on Earth, which is hardly extreme. Most of the atmosphere is made of nitrogen. There's also a few percentage of methane. So you have an abundance of carbon, hydrogen, oxygen, and nitrogen that can be accessed for growing food and life support. And furthermore, there are lakes of liquid methane and ethane on the surface of Titan. So if you think about something like the SpaceX Starship, which is designed to land on any world in the solar system with a solid surface, Starship uses methane as fuel. And the reason it does that is because you can make methane from resources on Mars. But Starship could also potentially land on Titan and extract methane directly from these lakes on the surface of the moon. Being close to Saturn, if we do develop a fusion-based economy in the future, which is, in my opinion, the key to opening up the solar system, you would have access to helium-3 resources from Saturn's atmosphere. Having exportable products like nitrogen, methane, helium-3 makes Titan quite possibly one of the more economically viable destinations. You have wind power on Titan. It's fairly low radiation. You have all of the protection of the atmosphere, and you're quite far from the sun. There's a global ocean of hydrogen and ammonia below the surface, and it may be that we can partly terraform Titan. Probably never warm it up enough to make it a place where plants and animals can grow, but perhaps we could, for example, clear out the smog. The smog that produces that orange atmosphere is made from hydrocarbons. If that could be cleared, it would warm Titan up somewhat, and it would give you a much nicer view of Saturn. Of course, Titan has some obvious downsides. It's very far away. It took Voyager 3 years to reach Saturn. It took Cassini about 7 years. So you would have to be fairly committed if you're going to visit Titan using chemical propulsion. And a significant communications lag. Fairly dark. At Saturn, the sunlight is about 1% of Earth, but on the surface of Titan, 9/10 of that is blocked by the atmosphere. So you've only got about 0.1% compared with Earth. Very cold, and also, like Callisto, fairly low gravity, even less than the moon. And that's it. Those are my 6 favorite destinations for colonizing the solar system beyond the moon. I think that that's where a lot of our attention will be over the next few centuries. All right. Thanks for listening to that.
That's great, Shaun. Thanks very much.
That's all right. It's on to me now to welcome our final guest for the day, which is Isaac Arthur. Isaac is a long-time passionate space advocate and creator and producer of the popular YouTube channel Science and Futurism with Isaac Arthur, which now boasts over 620,000 subscribers. The channel covers virtually every aspect of humanity's expansion into space, including development of the solar system, interstellar travel, space stations, Dyson spheres, extraterrestrial life, and much, much more. I highly recommend his videos. His content is a fascinating and absorbing fusion of hard science and imaginative science fiction. Today, we're going to show a video of Isaac's. It's called Outward Bound, Colonizing Neptune. So we're going to play that video next. Isaac, did you want to say anything before we start the video?
No, just that we can probably clip out the sponsor read at the beginning and and then we'll go to Q&A.
Yeah, sure, no problem. All right, I'm going to share my screen again and play the video. I can't promise that this will work smoothly, playing a video through Zoom, but we're going to give it a try. Hopefully, at least the audio will work. So let me try that now. Let's go to the browser.
Even though Neptune is 30 times further from the Sun than Earth, cold and dimly lit, it's still thousands of times closer to us than the nearest stars. And yet, it may turn out to be a great place to live and a gateway to those stars. So today we return to the Outward Bound series to look at how we go about colonizing icy giants like Neptune. We've looked at colonizing gas giants before, but mostly in the context of colonizing their moons, and not so much the planets. Ice giants like Neptune and Uranus are very common in the universe, as best as we can tell, and aren't actually that much more massive than Earth, generally only being 10 to 20 times as massive. Not like the bigger Jovians, which are many hundreds or even thousands of times larger. Indeed, their surface gravity, for a given value of Sun, Uranus has 89% of the gravity Earth does, and Neptune has 114% of Earth's gravity. Only Venus is closer, at 90%, and it is in some ways harder to colonize than either of these two planets. Akin to the Venusian sky cities, we could possibly build cities which float in Neptune's atmosphere. This, however, would be much more challenging to pull off because the winds on Neptune are murderous. Even on the planet Uranus, which has lower wind speeds in certain spots due, presumably, to this planet being tilted on its side, high wind speeds would still be a big problem. They are also potentially a source of massive power, though. Wind is tricky on Earth due to speeds ranging from useless to hurricane force. You wouldn't use a classic windmill on a place like Neptune, though. You'd use something closer to a jet turbine. Power is a pretty big issue for these outer planets because sunlight just isn't strong enough so far from the sun to be a viable way to power an entire colony. These planets aren't dark, though. They get lighting on par with what you'd expect in a room lit by normal light bulbs. We have some alternatives, though. We could also beam power out, as we discussed in the Power Satellites episode a couple months back. As already mentioned, we can tap the atmosphere for wind power, as well as the nuclear option. But what we really want is fusion, especially for these two planets as they have large stockpiles of helium-3, the preferred fusion fuel for aneutronic fusion. We will discuss why aneutronic fusion is seen as better than normal fusion in a moment. I mentioned the other power sources just to make it clear we have alternatives even if we never achieve portable fusion. But Uranus and Neptune in particular are both places we'd most likely hold off fully colonizing until we either did have it or knew it wasn't in the cards. So let's follow an intrepid traveler on a journey to colonize Neptune. It is the year 2400, and while Uranus has some basic stations on its moons already, Neptune only has a few small scientific outposts in its atmosphere, and on its largest of 14 moons, Triton, the coldest object in our solar system. We are colonists leaving from Earth on board a colonization fleet that's the first to feature fully functional aneutronic fusion devices. And as those rely on helium-3 for fuel, establishing some big helium-3 refineries in the outer solar system is high on everybody's list. We've had fusion technology for a while, but they are big and clunky power plants. And while those improved, they never got too good at powering ships. The problem with typical neutronic fusion, like that using deuterium and tritium, is that most of the energy from that fusion event is in neutrons, and these are hard to tap for energy and do a lot of damage to whatever containment system you are using. Aneutronic fusion is exactly that, fusion that doesn't produce many neutrons, but instead mostly stable and charged particles, which should be easy to get electricity from. Aneutronic fusion is far harder to do, but it represents probably the best path to relatively compact and lightweight fusion reactors, like the kind we'd like to use in spaceships or small colonies, places where mass and size matter a lot, and probably maintenance too. Someone went through the difficulties in inventing one, which opened the gates for us to the outer solar system, not just Uranus and Neptune, but all of the Kuiper belt, which is vastly larger and more massive than the asteroid belt. And indeed, it even opens the gates to the Oort cloud and other solar systems beyond. We now have a ship engine able to produce a significant thrust for days or even weeks at a time. our Neptune colonizing fleet, we will burn out toward Neptune at 0.2 G for half the trip, then flip over and burn down, arriving 5 weeks after our departure from Earth, and reaching a maximum velocity of 1% light speed. Like in The Expanse, we can use constant acceleration in place of rotating sections to provide gravity, though in this case, just a little better than moon gravity. But for a 5-week trip, that's fine. Now, as we've noted before, this constant acceleration approach is not usually a good one since it's very fuel wasteful. By preference, you'd accelerate faster, but not for as long, cruise, then flip over and burn down to stop. However, in this case it is okay because fuel and propellant don't matter too much, because that's the hypothetical maximum acceleration out of this style of fusion drive, 0.2 G, and that's probably being optimistic. So we just burn the whole time because it's not that long a trip. Indeed, we are quite capable of handling a much higher acceleration, as we are not exactly human. The fuel is fairly rare, but the propellant, hydrogen in this case, is very common, so we can blow it like it was going out of fashion. If we could accelerate faster, we would, and we'll talk about how we might later. But fusion drives and high thrust don't work well, at least not if you want a high final speed. We'd like to be able to do a full G, like we were standing on Earth, and in truth we'd like to do more, and we could handle a much higher acceleration. This is the 25th century, after all, and we've been picked to command this fleet because we are an experienced traveler and colonist. Few people in the solar system have been to as many of humanity's new worlds as we have, and we've made a career of colonizing planets over the centuries, and we've become more than a bit of a cyborg in that time. Long gone are the days of roughing it or making small outposts to slowly grow. Our fleet is carrying state-of-the-art, expandable rotating habitats with it, huge amounts of colonial gear, and most of those ships will be immediately departing to either pick up tens of thousands of more colonists from Earth or race off to the massive factories of the Belt, Titan, and the Jovian moons to pick up more equipment. We will need it too, because while we'll be temporarily housing people in those rotating habitats in orbit of Neptune, we are going to be building massive refining facilities right inside of Neptune's atmosphere. Indeed, it is going to be the single largest construct humanity has ever created. It will even outstrip the orbital rings of Earth. After all, those refining facilities are going to be similar to those rings, but Neptune is a lot bigger than Earth. See, there's lots of ways to mine gas from a gas giant. You can dive down and scoop it up, for instance. But we are going to do this with the biggest bucket wheel excavator in the galaxy, namely a giant ellipsoid orbital ring, which, incidentally, looks like a chainsaw. A chainsaw fit for a god like the one the planet is named after, Neptune's chainsaw. This is the 25th century. We don't do space colonization small or on shoestring budgets anymore. Billions of people live and work in space, and factories the size of small moons convert megatons of ore into products every day. Ships that dwarf the biggest oil supertanker crawl across the solar system delivering goods, and soon they will sprint, not crawl, as superior engines permit them to race across the void, fueled by the near-endless stockpiles of helium-3 on Neptune and the other gas giants. For now, many of those ships are carrying out segments of Neptune's chainsaw for assembly, and many of our passengers are not colonists at all, but folks traveling to view the historic event, the colonization of the last planet in the solar system. Truth be told, we find their presence rather irritating, standing around gawking and getting in the way, but this mission requires a lot of resources and backing, and spectators were part of the cost for that. One of them, on the younger side, asks us why it is such a historic event. We explain, until now, humanity has been essentially limited to using either stuff like uranium or thorium for fast ships, or dependent on powerful energy beams from huge collectors near the sun. Those work, and energy beaming from the sun is actually quite efficient, and part of this expedition will be making that system even more useful. But ultimately, we were dependent on those. We couldn't make massive amounts of power locally and in a compact way. In a generation or two, a small colony will be able to buy its own a neutronic reactor, cheaply fill a tank with helium-3 and deuterium, and have a reliable local power source. With fusion and some decent local manufacturing ability, they can set up anywhere they want, even way out in your cloud, and only need infrequent refueling. Nobody can threaten to jack up their power beaming rates or cut them off. A single tanker of what Neptune will soon produce will let a colony last centuries or even millennia without needing any new fuel. But why is the chainsaw going to be shaped funny, elliptical, not circular like Earth's orbital rings? Our passenger asks. Orbits come in many forms, including some rather peculiar ones. Almost every natural orbit is an elliptical one. If you can make a stable orbit, you can make an orbital ring that matches that orbit. You could even make some that wouldn't normally be possible. Our goal for the Neptunian chainsaw is to have an elliptical one that drops down into the atmosphere on its low portion and rises high up afterward. We will scoop gases up in big buckets which will enter the ring's transport system and be shoved along, refined as it goes for what we want, and raced up to fill tanker ships. Now we have options like this for Earth too. You could put two big circular rings around Earth connected by a third elliptical one. Indeed, that would keep the low portion of the ring just over the atmosphere and lower tethers down to suck up air. But what's interesting about Neptune is that its gravity is higher than Earth's, if not by a lot. And on the upper portion of that ring, it will be a bit lower. We can build domes on those sections with normal gravity and still get protection from micrometeors and radiation by the thinner atmosphere up there. Meteor protection matters too, since all the gas giants have rings of debris around them, even though they're not as big as Saturn's, and thus have lots of meteors. While there's not enough light there to grow most natural plants, it is enough to comfortably see by, though Neptune's day is only 16 hours long, so you'd want supplemental lighting. Fortunately, there is an effective near-infinite power supply right below, and Triton is almost as large as our moon and can provide plenty of construction and manufacturing materials after we've consumed its tiny siblings. Triton is the last and smallest of the large moons in our solar system, and actually has more mass than all the other Neptunian moons smaller than itself combined. If you head down deeper into Neptune's atmosphere, it's got interesting layers of clouds. Clouds on Earth are made of water, but clouds on some other planets can be made of methane, ammonia, or sulfuric acid instead. Neptune, though, is thought to have many different layers of clouds made of different things as you go down. Neptune and Uranus, which are small gas giants, but which you can also think of as ice giants, have a lot more volatiles proportionally than Jupiter has, for instance. Volatiles, things like nitrogen, water, carbon dioxide, ammonia, methane, and sulfur dioxide, are always of interest to us. And if we're willing to dive deeper down, we can find clouds of them for harvesting. We often think of mining space for metals, precious ones like gold or ones for construction. But these chemicals we need as the basic building blocks for life itself are very precious. Triton is also a good source for volatiles, and its surface is covered with these ices. But since demand is growing, and since mining that ice is more difficult than just scooping or pumping it up, it would still be advantageous, and indeed preferable, to mine such volatiles from Neptune's atmosphere. Now, we have a few ways to get down to those deeper levels. The first, of course, is to suspend yourself from a tether, hanging from Neptune's chainsaw, the orbital ring system that encircles Neptune we discussed earlier. The second would be to fly down in some interesting mixture of plane and submarine. The third would be from a balloon or even a giant turbine. A problem with using balloons on gas giants, as opposed to Venus, is that they are mostly hydrogen with a bit of helium, our two preferred lifting gases. You can't use something as a lifting gas inside an atmosphere composed of that. On Venus, we can even use oxygen as one because the atmosphere is made of denser gases. But Neptune is almost 20% helium, so we could use pure hydrogen, likely in plentiful supply, as you refine out the helium and helium-3. And you can heat it too, since we've got access to power. Or you can just run a giant engine and coast along with the terrifying winds. But you could also keep yourself pressurized like a submarine and drop deeper instead, to where you'd be buoyant. Hanging down from the tether seems rather neat though, and since the sun isn't really your source of light, there's no need to build flat. You don't have to make your orbital ring wider to support more domes, though you can. Instead, you just build up or down from it, or another supported platform. Hanging down is as structurally sound as building up like a skyscraper. The only difference is that one relies on tensile strength, whereas the other relies on compressive strength. So you could have hanging cities, lighting themselves, suspended over Neptune and down into the atmosphere, glowing in dim, dusky light, hanging down like immense chandeliers. Chandelier cities. A book series I'm fond of, Gregory Benford's Galactic Central Saga, references chandelier civilizations at one point, but I never got a description of them. I've always wondered if this is what he had in mind. I should ask him one day, but regardless, we shall call these chandelier cities, and they're ideal for ice giants. I imagine they'd be absolutely stunning to approach by plane, hanging there among the clouds and storms. But the atmosphere, while it gets much denser as we go deeper, is not the majority of Neptune. Indeed, it has a very large mantle, which is perhaps a dozen times more massive than the entire Earth, and which is composed mostly of the ices that make us call it an ice giant. With all that water, ammonia, and methane ice, it is massively rich in the building blocks we need for artificial ecosystems. Getting down there to mine it would be tricky, but active support, like our orbital rings, can be used to make stuff much stronger against crushing too. However, it's quite likely it rains diamonds down there, and we could get quite deep just relying on strong materials. Because of this, we'd be able to harvest a lot of that diamond and possibly other materials, or even get to live in diamond-hard domes deep down in Neptune. I should note, though we always hope the future will be peaceful, that these sort of buried colonies, hidden and shielded by huge atmospheres, are good places to live during conflicts. For that same reason, you could see a lot of rotating habitats bury themselves deep under ice or rock in asteroids and comets, or import a lot of hydrogen and helium, not just as a long-term fuel supply, but additional shielding. They can wrap their habitat in cheap tanks of gases. It's hard to drill deep into the Earth, not just because of the pressure, but the rising temperature, but it's not as bad inside Neptune's mantle as it is in Earth's. Eventually, there is a core, which is essentially a rocky planet all of its own down there, but you probably have to remove that atmosphere to get to it. We'll talk more about mining planetary mantles and cores in our Earth 2.0 series, which will start next month. For ice giants in other solar systems, ones nearer the sun, as some might well be, you might blow that atmosphere off and use it like a rocket flame to push the planet into the sun's habitable zone, and be left with a rocky planet when you're done, which is ready for terraforming. For this, we could employ the fusion candle we discussed in Colonizing Jupiter. We are not expecting to do that with Neptune, though. The long-term plan is just to build more Neptunian chainsaws and regular circular but wider orbital rings around it till we encompass the whole planet. This is something we call a shell world, and we discussed it in more detail in the Mega Earths episode. Even for advanced civilizations living in the 25th century, building a shell world around Neptune would take a really long time, but it can be done incrementally, just adding more rings and chandelier cities till you encompass the whole planet. Then add dirt and water and lighting, potentially sun moons orbiting once a day, vast fusion satellites producing light. We have the power supply for that and such an enormous construction project. And as we mine Neptune's atmosphere and mantle, we can slowly contract those rings and therefore contract the shell world too, keeping it to a size that provides normal Earth gravity. Incidentally, even if you eventually expanded your orbital rings to make a complete shell world, you could keep those chandelier cities we mentioned earlier hanging down under the shell. They might also work very well on planets or moons with icy shells over deep oceans, like Europa. Neptune's own moon Triton might have a subsurface ocean too. There is a lot of gas on Neptune, and it raises the question, what would we do with it all? For that matter, with Uranus being closer, and maybe easier to mine with its lower winds, who is buying our helium-3? Well, first, the helium-3 concentration on Neptune is 19 parts per million, which is a little higher than Uranus's 15 parts per million helium-3 concentration. But second, in a fusion economy, that extra distance to Neptune from the inner solar system, as opposed to Uranus, is actually fairly irrelevant. Indeed, parts of the asteroid belt will sometimes be as close to Neptune as Uranus, and this difference in distance doesn't much matter anyway. It's a minor amount of delta V compared to the energy that fuel contains. Tankers carrying helium-3 and deuterium would still move slow. It won't spoil and has a high energy density, so there is no reason to move it quickly and waste energy or capital on very large engines. Moreover, though, we'll be seeing a lot more people moving to the outer solar system now, particularly the Kuiper Belt, where land is cheaper and plentiful, but they'd have to bring their own sunlight. And as rarely as one would need to bring in fusion fuel, folks can wait a couple centuries till Neptune is closer to them again on its own long orbit to refuel themselves. But when asked, our traveler, admiral of this colonial fleet and figurehead governor of Neptune, says that it's really all about ships, and not just ones with aneutronic fusion drives. See, you can bounce a laser off a sail and make it go further away, or even off to a side, by tilting the sail to bounce the light at an angle, but you can't move just sideways or inward toward the sun, not by bouncing alone. What you can do, though, is bounce a beam off something further out, and bounce it back in at your light sail, pushing you back inward toward the sun. The problem is, if you stick a mirror further out than your ship, you will push it away eventually. So it helps to have that mirror on something that is massive enough for the recoil to be negligibly small. Ice giants and their moons are perfect for this, as are larger icy bodies in the Kuiper Belt. They can also emit their own beams rather than bounce, if they have a power source. Had nobody invented good, cheap aneutronic fusion, we could have gone about colonizing the outer solar system this way, beaming energy out from massive solar collectors near the sun, and using those, bounced back, to push ships inboard, and to power these cold, lonely pushing stations. Even with fusion, though, it's still a nice path, because it means ships need not rely entirely on onboard fuel and propellant. Indeed, the combination of the two will allow even better and safer and cheaper interplanetary travel. We said that this sort of fusion drive really only permitted a maximum acceleration of 0.2 g, and there are ways that could perhaps be boosted, but it could pull that while getting beamed energy, or even beam propellant, out to the ship. So you'd get laser highways inside a solar system folks could use to supplement their engine, but they could still operate without them too. It would be like jumping in the fast lane, and gives the benefits of both systems while removing many of the limitations of and dependence on each. Our traveler turned admiral turned governor, though, has even bigger plans than chandelier cities, planetary chainsaws, show worlds, and giant mirrors. Indeed, even plans beyond colonizing the Kuiper Belt and Oort cloud. Our governor plans to colonize the stars themselves. He tells our young tourists that one day the moons of Neptune will be giant shipyards, turning out colonial fleets to head out to the stars themselves. Armadas that will be built here and launch, not out to the stars, but in toward the sun, pushed by beams toward it and then sail past, pushed even faster by stellasers near the sun, running up to decent fractions of light speed, then back out again, ever faster, pushed on till they reach the Kuiper Belt, and then pushed even more from relays and lasers out there. Then they will cruise along ahead, massive interstellar arcs lit and warmed by fusion reactors, sailing off to more distant homes. Neptune, we tell our young passenger, will be the gateway to the deep ocean of outer space, the last big port of call, and it may be big indeed, with vastly more size and resources than Earth, with a near endless source of power, with all those moons and its own rings and Kuiper Belt nearby. It could become a massive kingdom fit for its namesake. If our young passenger returns to Neptune when they're an adult, they'll see a growing empire that they can reach in just a couple weeks' travel, and quite cheaply. It's an empire the governor himself will never lead. Once it's built up enough to build its own fleets for interstellar travel, he means to be on one of those, and tells our young passenger he hopes they'll join one themselves one day. The solar system is now a much bigger place, opened up far past the asteroid belt for settlement, but it's just a tiny corner of a vast galaxy. While not the last frontier of our solar system, Neptune is the last truly big one, and it's fitting it should serve as the gateway to the stars. So this is not the end of the Outward Bound series. We still have
You go ahead and stop there if you want.
Yeah, I'll pause it there. That's fantastic. I love that video. It really gets you thinking big, doesn't it?
It was probably one of the funnest ones to do, though, of course, it's pretty far out compared to the rest of the series, which is more Mars or Venus and then relatively near time.
Yes. All right, we will now go to our Q&A session, which we've allocated half an hour for. I will open it to the viewers to offer their questions. I'm not sure if we have any on Facebook. Let's have a look.
That was a solid video, Isaac. Now we have to go to Neptune even more now.
What's funny is, like, right after we got done talking about that, we go talk about the Earth 2.0 series, we get to sea studying. And this was pretty much the next episode after that, and colonizing the oceans, and it goes into the footage from Ripple with the launch for the rocket that I got off you guys from that. So.
Oh my goodness! Oh man, this is a small world. Too real, man. Too real.
There you go.
But I like that the content's being. I'm glad that the content's being reused, though. You know, it's keeping the conversation still moving forward. You know.
And it was good animation too. The fellow who did a lot of the Neptune ones also did a nice one of what we said, hexagonal fit together, sea studying things. You could just poke your ships together for a land base. So it was interesting.
That's right. Yeah.
Adriano, you're muted. Adriano, you're muted. Adriano.
I think he might be talking to somebody else.
Oh, is he? Sorry.
Yeah.
You're right there. Does anyone have on the Zoom chat have questions, including any of the panelists? Is there
sorry. Okay, now I'm muted. Thank you for reminding to me. So no, I just wanted to ask Shaun and Jerry that are excellently chairing this meeting to give the floor one per time in order we can go shortly to the end of this meeting that is already 1 hour longer than what it was expected to be. But I understand that we like to have a conversation now, therefore it's better to do it. However, just want to say this, that on Facebook, we are always having some problems. Last time we broadcasted to Facebook SRI main group, and some people cannot see it. Today we are broadcasting to the event, to the webinar event, and some other people cannot see it. So so I don't know what to do. Maybe next time we will go directly to YouTube. That is maybe a safer platform for broadcasting. However, having said that, just a few words before we start the conversation about the meeting of today. That for me it was quite very much inspiring, and all the presentations were very high profile. So thank you very much for all what you presented today here. That's really a piece of knowledge, very important for our Congress and for our evolution and development, because you know we at SpaceRenaissance like to learn. Each time we make a Congress, we like to learn things from our panelists that are really helping us to leading the SpaceRenaissance movement. This is the important thing why we make Congresses, not only to I don't know, to appear. Eh? We want to learn and understand and keep lessons from what we are learning. So just a couple of things. 5 years ago, more or less, Jeff Grison told us that when the cost to transport one human being from Earth's surface to orbit will be less than 1 million per seat, then it will become more convenient to have humans working in space than robots. Now, I think from several videos that I'm watching about SpaceX, Starship, and all this kind of developments, that with Starship, that is the first fully reusable rocket, fully reusable vehicle, we will reach this goal and maybe lower. So that means that we can start really expanding to having a civilian expansion into space. First thing that I wanted to say. Second thing, if I think all of us watched the TV series The Expanse, and maybe also read the books from James Corey. So if you see the TV series The Expanse, you don't realize the physical differences between the Belters and the Martians and the Earthers. So, but reading the book, these differences are very much better explained. So the Belters that were ground in low gravity are more than 2 meters tall and very weak bones and exile constitution. And when they come to Earth, they cannot stand because they are too weak. And the Martians are a little bit more, you know, more than more strong than the Belters. However, they are weaker than Earthers. So James Corey, or better, the two writers that write these beautiful books, gives very evident the physiological differences between among people ground in different gravitational environments, and not only the physiological problem but also the social issues that will come from that, because you know that even on Earth's surface we have problems, issues between different skin colors and all this kind of things, let alone to imagine what it will be when we have different shape in our bodies for the social problems, etc., etc., etc. So we at SpaceRenaissance, we are humanist. So we are caring very much that the expanse will be as smoother as possible, and possibly for some centuries and maybe millennia, that our body shape will not change too much and too much quickly. That's why my personal preference is for the O'Neill model, but that doesn't mean that we have only to apply the O'Neill model around Earth and the Moon. We can apply the O'Neill model everywhere, as several of the presentations that I saw today were saying. So my concept would be, let's work on the surface of planets and moons and live inside O'Neill cities. However, since we cannot claim to say, okay, this is better and it must be done because we don't know which kind of development the civilization expansion into space will which road it will take, if we will go firstly to Mars or firstly to the Moon or what else. My last word on this is that every possible road will be better than not to go. Mm-hmm. Therefore, I will be very happy if we start making a city on Mars with all the recommendation, the possible recommendation about human physiology and social problems, etc. Or if we will make a Crafteric Selenopolis, or if we will make first the O'Neill Iceland one, or as Jerry so clearly proposed in his presentation. So what I say is all of our recommendations are good. The really important point is that we start going. And this is the point, the political decision that we have to try to make more evident to all the Earthers now that are struggling with the COVID-19 and with the other crises that are trying to strangle our civilization and our real human nature. So thanks everybody for your presence here today, and please let's go ahead with your questions and discussion.
I love the fact that Earther has now become a mainstream term. James Corey can be attributed to that. Chris, did you want to say something?
Yeah, I would. Adriano was actually great in setting me up. One of the things I wanted to share with you is that my company, Digital Habitats, is working on a number of design issues that are related to space and otherwise. Isaac and I talked some time ago about seasteading variations, which we now call aquacities. So in our architecture, we're looking for how do we do sustainable planetary and space development under one model. And one of the key elements in our economic challenge is that we're developing the starports that will be needed for starships. And at the same time, we're also engaging in the Elon Musk sponsored X Prize for carbon removal. So we're looking at how to make star flights, starship launches, massively carbon negative, provide a funding model that will allow us to have zero launch costs. And so one of our conversations that I want to have with you guys, and I've been talking to Jerry behind the scenes, and I'm happy to set up a Zoom session for us all to chat afterwards, is what happens to all of our assumptions in the space community if we can, in fact, offer zero launch costs, and that ultimately we're looking at the potential of having 100 megatons in orbit every year from only 100 starships. So Adriano's dream, I'm looking at actually achieving this decade.
Amazing.
Anybody interested in that conversation?
Chris, Bruce Mackenzie here. Do you mean zero cost launches or do you mean carbon neutral launches?
Massively carbon negative, right? So there's one angle that we're discussing. For example, I'll share it with you.
But there would still be a cost for energizing the starship.
No, $0 launches on selected projects. So just like you have the Dear Moon project where Izawa is saying, I'm going to pay the freight, part of our business model is to find projects that we consider of significance and basically pay SpaceX to put them into orbit.
All right. Well, then there's still a cost because there's still somebody still paying.
Right. A cost to us, not a cost to you.
Right. Okay.
So for example, the simplest discussion is if you bought four launches, then that would give you the same amount of mass as the ISS. And Daniel, as I've also said to you behind the scenes, what I see the conversation now shifting to is instead of all of us focusing on space-based mining and construction and resource and all of that stuff, which was really a gravity well conversation, we want to instead say, how do we exponentially lower the cost of payload from Perseverance being about $2 million a kilo down to $1 a kilo?
Yeah.
So it now becomes how do we do the construction so that the payloads are free?
Okay, so a major thing that has to be remembered in all this is that the cost of spacecraft is mostly not the spacecraft. It's the cost of paying the people who design
labor
and the
labor to make these advanced materials.
The spacecrafts themselves are not made out of such exotic material that they actually cost billions. But when you have over 1,000 people working for over 5 years on a project, that's what mounts up, isn't it?
Yep. And to that point, one of the things that Digital Habitats is trying to do is to digitize the planet, and that includes fully autonomous manufacture on Earth to solve Earth problems of housing and transportation. So exactly what SpaceX is looking to do for spacecraft, what Tesla is doing to do for cars, we're saying this is an automation wave that will encompass the entire planet. And then as a byproduct, that means that all of those human labor costs will get baked into the overall cost of exponentially increasing our manufacturing capability. And Jerry is also right in that there's an implied concept here when you're looking at a Perseverance rover, which is cost is exponentially related to complexity. So while we're doing our first in a series and we're doing R&D and all of that, of course it's crazy money. But as we look at applying Wright's law, or we look at different kinds of payloads, then, you know, there's a possibility of being able to get stuff in space. So we're hearing a lot of conversation here about, you know, mining for water. And I'm basically saying, well, water is ostensibly free. Why not load a Starship up with water and say, there you are, it's in orbit? Right? There's no complexity, there's no testing. So if you're trying to build an island one type structure, why not literally extract atmosphere and water and all of the materials you need for life, put them in orbit in massive quantities, and then use that as a starting point for building these space colonies, which are ultimately self-sustaining. They're mini Earths.
Well, a major thing about developing the space habitats, and Island 1, for example, was that it was predicated on the extremely low cost of getting materials up to orbit, which was going to be afforded by the space shuttle. And of course, that never happened. And the initial...
And a lunar mass driver.
Yes. Yeah, but, you know, I mean, we can build mass drivers. That's not a problem. I mean, they built MIT that did, what was it, 580 G? But we need, what will kickstart the whole thing is cheap access to Earth orbit, so it can take up the very, very initial materials to get the whole project started.
I think an element that's being missed. I think an element that's being missed in the conversation is that the reason why SpaceX is going the reason SpaceX is able to market Starship as a $5 million some odd vehicle is because they're trying to bring certain metrics of reusability reliance that we've only seen with ships and airplanes now, and like if you wanted to get to that $0 cost to put things into space, you gotta be able to create rockets that have an equivalent metric of reliability to an Airbus, you know. And this is why, and that is why airlines are able to successfully and safely market that their planes only cost $5.88 per seat per mile in the airplane, because they know that they've already reached a level of competency in their technology that allows them to market the plane at such a cheap cost to the operator, and then by then the passenger, again from a business model standpoint. And we need to do that with rockets. You know, SpaceX want these rockets to be built en masse, and
the number of flights and for how many decades.
Exactly. Yeah, exactly. And time between overhauls, and those things get accounted for.
Yeah. Bruce,
folks, I'd like to hear from any of the audience on Facebook. I don't have access to the chat, but we could talk for hours. Let's get audience questions. Thank you. And I could take the wind turbine or the vernal sphere if people want.
Isaac, did you want to say something?
If they got questions from Facebook, I'll be glad to do those first.
So, Shaun, do you want to have a look through what's out there? And
sure. So,
okay, we have a question. We have a question. Sorry, we have a question from Facebook, and it is a question for Daniel Cottitta. It is: would be a small 4 to 6 passengers sea-launched rocket be feasible?
Yeah, affirmative. Robert Truax that was his attempt at making sea-launched rocketry feasible, was doing a suborbital, at best a suborbital vehicle that was meant to compete on the X Prize program, again lifting 4 to 6 people into orbit or into suborbit to 100 kilometers, and that would have incentivized further investment to a larger launch vehicle development. So that is possible, but I think in the long term, sea launch rocketry is best seen as a cargo mover and not a passenger mover. As much as that the feasibility is there and viability is potentially there, even as like a potential, even as a point-to-point seed launch rocket, you know, that's been conceptualized again by Truax. Like all the information's been there, and that. But again, in the long term, the business model pointed toward a cargo exclusive ship that can move hundreds of metric tons into orbit and do it all over again. So the short answer is yes, it can be done, and the long answer is it wasn't intended to last very long. Like you can do it, but it won't make you money in the long run.
That's great. I've got a question here for which I think is best suited to Isaac. What is aneutronic fusion?
Oh, loosely speaking, there's a lot of different models for it. It's just the idea that you might be. It's whenever we talk about the moon and wanting to harvest helium-3 off of the moon, that's the motivation for it. Helium-3 is seen as a very good feedstock for aneutronic fusion. And there's a lot of debate as to whether or not that would ever be a method you could do. It's like going to be harder than deuterium-deuterium or deuterium-tritium fusion. But it has the advantage that when you're doing it, it's giving off beta particles, not neutrons as the main source of power. It's a lot easier to handle things like that than it is to handle a neutron, which is a big electrically neutral object that's slamming things, you know. A neutron bomb is a very good weapon for killing people because it's got that kind of energy involved in its neutrons. Pretty much for the same reason it makes for a less than ideal reactor. So a lot of our fusion reactors right now, our big problem with them is all those neutrons they give off make it hard to make them stable. Aneutronic, which is probably harder to do and might never be doable, is a lot better, especially for options like really compact ones. If you're looking for the personal rocket ship, the Millennium Falcon equivalent, it probably needs to have something like an aneutronic reactor to be viable. And that's why we set that episode the 25th century. So not 20 years in the future on that one.
Helium-3 is the lowest temperature aneutronic fusion. There are other aneutronic fusion reactions, but they require larger nuclei and therefore much higher temperatures. So you can, as Isaac said in his video, you greatly reduce the mass of your reactor because you need a lot less shielding with aneutronic fusion reactors. So that's very important for a spaceship or a space settlement.
Shaun, if I could give background on sea launch. I believe the sea launch was a proposal for an incredibly massive rocket, possibly built in a shipyard, and it would be just so large it wasn't practical to have launch facilities. You couldn't tip it upright, you couldn't have a launch tower, so they would tow it out to sea, tip it vertically in the water, and light it right out of the water. And it would.
You're doing my job. I should be explaining this.
But the important thing is it would save a tremendous amount on the land-based infrastructure.
Yeah, no kidding. The studies from the Smithsonian showed Aerojet wanting to take over what is the now Mosquito Lagoon north of Kennedy Space Center and overhaul all of that into a Sea Dragon launch vehicle development and manufacturing and operations facility, literally an all-in-one. And by that, a quasi seaport of Central Florida. Those plans never made it into fruition, because now the Mosquito Lagoon is a conservation area of the Space Center. And that's fine with me, quite honestly. There are so many other parts of our globalized world that can do this type of launch vehicle architecture still. At least a dozen sites I can name off the top of my head without having to create new land or new facilities. Just approvals and permits by existing city councils and private owners of that land and piers and shipyards to do that work on and work with in that sense of cooperative effort.
Just to extend what Daniel's saying, if you look at the idea of what SpaceX is going to do with its floating starports, and we're also looking at building several hundred of these things in order to do the suborbital star flights, so what they call point-to-point. This is going to be a transformation, as Gwen Shotwell talks about, of the current aircraft industry, provide a terrestrial option for disrupting transportation. And of course, the reason why they're floating is because you have to be a certain distance from the metropolitan area. But one of the things that is often not discussed is that the minute that you put them at sea, you get out of the challenges of real estate, the things that Daniel just described, permits and regulations, and instead you're operating under international maritime law. And my sense is that this is going to make it much easier to literally sail your starport to the point of opportunity, and that we should actually be stopping all land-based spaceport development in deference to this kind of model, because it's coming in any case.
Right. I mean, yeah, that was, I mean, the comments of permits and acquisitions and acquisitions, permissions to do super heavy launch vehicle development. The end note, the end takeaway is that it will, again, it's using existing places of opportunity, existing manufacturing hubs, companies, enterprise, and economies to build up these types of vehicles, and then you're able to send this massive rocket out to sea, where you didn't need a launch pad because you got this ballast, because it uses a ballast tank below the rocket to tilt it up skyward and launches, and you're only using boats at that point, boats and a ballast tank to launch a super heavy launch vehicle. At only 40 years ago, you needed to conceive over $7 billion worth of development just for the launch site and stuff and such. So again, that's added perspective that, like, Musk has not successfully escaped the financial equations of it all, because he has to make 100 some odd starports to do these launches from, and he's still tied to U.S. law under maritime law, because they are American, because they are built in the U.S.
Well, that's actually an interesting point, Daniel. We're proposing that the destinations build the starports in the same way they build airports today, so that they commission local work and local shipyards to do the construction, and that we leverage the petroleum industry's excess oil rigs and other equipment, and basically create a shipbuilding boom in this, and don't put the burden on Musk to do it, because arguably we're trying to create global infrastructure in preparation for this. So why not let the planet pay for it?
Something like that, yeah. There's been at least 5 other methods to make a whole lot of money without having to tap into carbon excessive or carbon extensive plans, essentially, where there's opportunities everywhere.
2 different issues. The carbon discussion is a climate activism, so it's aligned with global issues. What I'm really speaking of is that it's global infrastructure that we're building, and that we should look at distributing those costs to the ports of call. So for example, we're talking to Dubai. They're like, we'll build our own, thanks. We don't need, what hasn't been discussed is everybody's talking about it for suborbital, but Musk hasn't discussed who is going to build the starports. And this is a business that we want to get into now.
Right.
He's going to build one on Mars. There's one more question. We obviously have a lot of interest in the sea launch. From Thorsten Frank, what do you do when there's heavy weather conditions in the oceans during launch and eventual landing?
Yeah, so the paper, as again, all reference at this point, we've generated our own reports and worked with universities in the modern day in the last 3 years to get new data, and that the old work is mere reference and what to work toward at this point. Sea launch vehicles were slated to be rated to work in simulation through photos at the archives showed that they were able, the sea launch vehicle structures were rated to operate in sea state 5 and 6 conditions. So we're talking relatively high waves due to the size of the structure of a super heavy launch vehicle, and crosswinds in excess of 32 knots. So it's a higher margin. It's a higher margin than than for land launch vehicles, and I'm okay with that.
I'd like to point out that we shut down Cape Kennedy when a hurricane comes in, and there are places in the world that have almost no hurricanes, especially along the equator. That's all.
Yeah. there's a
lot to be said about launches from the equator for not just space elevators. So
right.
There's portability. If you can move your launch site, you can move it to where there's more launches being done too. You know, you're talking about moving out the industry. We don't launch away from cities because, well, we don't like cities. We launch away them because rockets are really loud. So,
Yeah.
you know, you want to be able to bring things in, you potentially then just take the whole thing, set it up, get all your heating done, all your transport done for the factories from the city, and then let the sliding platform go back out to sea and do its launch the next day.
Exactly. And that's what's important, is that we're taking those inherent environmental risks again that are vulnerable to people and animals and infrastructure. And again, it's designed for a vehicle architecture that was meant to exceed the Saturn V. So, that again justifies and quantifies the advantages of ocean launch vehicles, is because you're taking those very caustic elements of launch vehicle operations, and they're omitted because the ocean's a really great insulator of vibrations and acoustics, as well as distance away from your infrastructure, even the boats themselves, to further compound that.
And then the advantage of sea launch is obviously that you can go to whichever latitude is appropriate for the type of launch you want to do.
That's right.
If I could change the subject, there was mention of Venus and terraforming Venus. You could, with orbital industry, construct a giant solar reflector the size of a planet and move it to the Venus-Sun L1 position, and it would shade Venus.
I think there's a good video on it.
But there's a caveat. The Venus atmosphere is so thick, it's a good insulator. So it would take a long time to cool down. And if anybody, I have a few ideas that might make it speed up more quickly, but it is a really long-term project.
I would absolutely love to talk to you about those at some point at your convenience.
And guys, we can talk for hours. Let's get a variety of subjects on, things related to space, not just launch.
Right.
And we'll leave fairly soon.
Would Mercury then would Mercury be a good candidate to be mining, or to say that you had some say that the ISRU components were moved to Mercury to build, say, the shade panels for a massive array to block Venus, the sun from Venus with? Does that work out? Would that be good?
So I would recommend a metallic asteroid.
Okay.
Get a belt, maybe cover it with wax, sputter the metal onto the belt, evaporate the wax, and you can just extrude a very long panel of incredibly thin metal. I believe Eric Drexler might have a patent on that expired 20 years ago.
Of course.
Bruce, on your question about terraforming Venus,
yes,
I've inserted a link into a chat from a fellow named Anton Petrov. No disrespect to Isaac, but he does a lot of great space stuff. So he's got a two-parter that literally talks about changing the rotational speed, all of the issues. It's very well thought out. I suggest you take a look at it.
Thanks, that's great.
Bruce, talking of Eric Drexler, I'm interested in trying to contact him with regard to the space project, because I'm sure there's a lot of input he could give. I discovered that I don't know if he is still now, but at the time, he was working at Oxford University here in the UK.
I don't know that. If you cannot find him at all,
Nano construction.
So if you run into a complete dead end trying to contact him, let me know. I know people who do know him. So
right. Now there's something else which I'm in touch with Tasha O'Neill, Gerard's widow, and she's given her blessing to the space project, and she says it's so good that people are carrying on looking at Gerard's ideas. And something that I meant to ask her and didn't get a chance before today, but then there wouldn't have been time to have asked it anyway. His question to the students: is a planetary surface the right place for an expanding technological civilization? Was meant to be the first of a number of questions that the students would discuss during their time at Princeton. But they never got on to the second question. They were so involved in this. And I wanted to ask Tasha, did she know what any of the other questions were?
Okay, I know a little more about that, partly from books, and I also had the privilege of helping Jerry a few times. What I heard was all of the, so he was a high energy physicist. He had some books and patents written, and all the physics and professors had to take turns teaching freshman physics. It was just an obligation of being a professor. When his term came around, you know, he had all these board students. It was Princeton University, a liberal arts college, very elite. The Vietnam War was going on at the time, I believe, and these students were asking, what is the importance of physics? You know, how does it change the world? You know, why should I study this? And he offered out-of-class discussion groups that started out with the importance of physics. And one of the questions he asked was, where is an important place for people to live? And he thought he was going to be teaching about centrifugal, you know, forces and equal and opposite and pressures and things like that. And they came up, he was kind of expecting them to decide that Earth was the best place. But it turned out that you have so much flexibility with these big settlements. You can spin them at any rate you want. They can be positioned anywhere in the solar system, and unlimited solar energy. And they calculated the mass of the asteroids, and known at that time, and figured if they used all those asteroids for raw materials, they could have 3,000 times the Earth's land area, and it would all be climate controlled, including agriculture. And so that just kind of became the dominant thing for that discussion group. And he ended up writing the High Frontier book and going on a lecture tour. This was way before the internet. So.
Yeah, well, I met him when he came to the UK and spoke at the British Interplanetary Society. And in fact, I was one of a small group that took him off for a meal after his lecture. And I'm very pleased to say that I still have my personally signed copy of the High Frontier. And
I lent my personally signed copy to a student under great duress. She was really pressuring me. And then ISU ended and she went home and took it with her. I put in the chat ssi.org. It has a lot of Jerry O'Neill's work still there.
Please, may I have a floor?
Right, yes.
Okay, so while we are going to close, because we are already 3 hours, and I think, okay, we can continue this discussion in our next appointments, our dates and webinars and the Congress, etc. But before leaving, I just would like to deliver a few more questions to you for the next time, and for these are the basic questions we will try to respond with our Congress. And the first thing is a recommendation, because I don't know if we really are reflecting deeply on the disruption that the new space sector is doing in the space economy and the space development, etc. I mean, who could think just 2 years ago, I'm not talking about 10 or 15 years ago, that we will have in 2021 the development of the first fully reusable vehicle. But SpaceX is doing that. And this, so why I'm saying this? Because every time we come to try to foresee a reasonable timetable for civilian space development, we see that our discussion is trapped into two opposite views. One is still an old space view that think about difficulties, technological, financial, etc. But the world is changing. Even the global finance will be changing very much after COVID. I'm sure of that, because we have the electronic money. We have a lot of things that pushes to another way of conveying money on useful projects. I just say this, but I don't want to go more deeply in this kind of discussion. However, so. Let's think about, in the view of our Congress and the symposium discussion that we will have, what it means, the new space industry and market development, with the achievements that we can have to lower the cost to orbit, to bring people there, etc. First thing. Second thing, but I'm not asking you to respond now, otherwise we will have another 3 hours discussion. Second thing, let's think about civilian development. So we were attending to the beautiful presentation by Susan Jewell about education for astronautics. But I would ask to Susan to consider adding to her program, to her beautiful program, to think about civilians, education for civilians to go to space. That will mean that we will have more advanced technologies for protection from cosmic radiation. We will have artificial gravity, finally, I hope. We will have green environments in the habitats. We will think about civilians in space, not just military trained astronauts. So this is something that we, even if we talk about colonizing and settling space, we are still always trapped in an old view of space. That is missions requirements, exploration, and to really think about settlement is hard. It's hard to imagine, it's hard to figure out how to do it, etc. The third point, and last for today, is evolution. So we know about the Nikolai Kardashev scale for type 1, type 2, and type 3 civilizations. And we know that to step from type 1 to step to type 2, we need to become able as a civilization to exploit the energy of the solar system. And Bob Zabrin added another criteria, that is the resources of the solar system. And Carl Sagan added another criteria, that is information that can be exchanged in the solar system. And myself, because I am a very presumptuous guy, and I claim that I am pushing ahead astronautical humanism, I think I added the fourth criteria, that is social inclusion. Only a solar civilization can be fully inclusive, because 8 billion people cannot anymore make it on one only planet with the resources, the energy, and the information, exchangeable information on one only planet. So we need to step outside in order to become a fully inclusive society that means that we will give to all of our citizens, whatever the number, because when we go outside, we can become trillions and not be any more concerned about being 10 billions. Okay, so to all of our citizens, the real opportunity to realize their highest Maslow goals, self-realization. That's very much more than the lower Maslow goals that are everybody can eat and everybody can dress and everybody can have a ceiling on their head. So a real utopia to can be able to aim to the maximum levels of the Maslow scale. So finally, civilians, evolution, and the first, what is what? Yes, the disruptive contribute of new space to the civilian expansion. So with this, I know that you would like to discuss about that, but I prefer to invite you to our next discussions and webinars and to the Congress. Please register to the Congress. I will add the links if you don't have it yet. Submit a paper. The same thing you presented today. You can present in a symposium to the Congress and have a Congress discussion there, and contribute your paper to the ACTA that will be made, the book of the ACTA that will be made after the Congress, and so on. And last but not least, join the SpaceRenaissance as a member. Okay? So thank you everyone for participating. See you next time. And
thank you everyone.
Ad Astra.